Okay, we can start the workshop so to not have delays. Welcome everybody, and we are organizing in IROS the first aquaculture dedicated robotic workshop. And the goal of this workshop is to bring both the industry and academia and understand the challenges that the industry is facing and try to see what kind of solutions we have so far, and then inspire the community in order to bring new solutions. We have a big program. It's only few hours, but intensive. So 2 sessions, 2 panel discussions. We have several spotlight presentations. And at the end, we will hopefully discuss the remarks of this workshop. So the invited speakers in the first session will have 4 people, and they will give the industry perspective and the challenges from the authorities in general. And in the second session, we have people working in research, and they have developed solutions in aquaculture. 2 sessions, each of them from spotlight presentations and dedicated poster sessions that will be on the breaks. They will discuss some relevant results in aquaculture. On the panel discussion, they will be all invited speakers, and we will not have questions during each invited presentation, but we will have all the questions during the panel discussion. This is the organizing committee, and I would like to welcome you all from on behalf of the organizing committee, and we have a support from 4 technical committees for this workshop, and there will be 3 awards, as we will see later, and we have also launched a special issue in the Frontier in Robotics and AI. So as I said, this is the program. I want to be very short so we don't have delays on it, and I would like to start the first session and give the word to the chair of our session, Svein Ockrems from Ocean, and then he can chair the session. Welcome all, and thank you.
Thank you. I would also like to mention the name of the previous introductor. It's Eleni Kalasidi, also from Ocean. And thank you all for attending. I hope we have and I believe we will have a very interesting session. Our first speaker today is Kristine Størkersen from Ocean. She will talk about current and new farming concepts in the aquaculture sector. There you go, Kristine.
Thank you. I noticed that I need to keep the mic close, but can you give me a hint if you don't hear me?
I will do your presentation.
I'm Kristine Størkersen. I work at SINTEF in Norway, and I'm a safety researcher. So I'm not going to talk about robotics at all, or nearly not. So my message is, this is the message today. When you create technology, you need to remember to think about how it will be used in the work situations, in the workplace. When you try to, because all people making technology usually want to decrease risk. And when you do it, it can actually induce new risks. But if you think about the context and the working conditions, you can avoid that. So my coworkers and me, we have been researching the safety and salmon farming for almost 2 decades. And safety is about how to work without getting injured, how to work off the plan. And to understand that, you need to understand the working conditions. So these are interesting times in the aquaculture industry, at least in Norway. New workplaces are created. New technology, new farming concepts like these. Some of these are still dreams or being developed, while others are actually up and running. And we have been studying how safety is, how you work safety at displayed. Most of the aquaculture facilities in Norway are simpler than this. But when we talk about aquaculture in Norway, we usually talk about salmon farming. And this is a typical salmon farm today. You have the rings with the nets below. So it's open production in net pens with a feed raft, usually. It's quite simple technology and quite cheap technology, at least compared to the salmon prices. So this is a very profitable industry for Norway. It's very, it's giving a lot to the country, and it is bringing a lot of workplaces for Norway. But together with the workplaces and the profit, we have had major problems, I would say. So even if we have solid regulations, and each farmer needs to have a permit in how much salmon they can produce and exactly in which places, they will have. We still have quite an intensive production with a lot of challenges. One of the challenges, the largest challenges, is the salmon line. That is infesting wild salmon, and also mandatory delicing make the mortality of the farmed fish high. And sometimes the farmed salmon escape, and it can go into the stocks of the wild pure salmon, which the Norwegians don't like. And all the good salmon farms sites are also occupied. The farms are quite close, and they risk spreading diseases to each other. So this is the motivation for why we have all those new concepts coming in, and it's much of the motivation for the technology development. In addition, I would say, or I hope that some of the motivation for the technology development is that it's a very dangerous occupation. It's actually the second most dangerous occupation in Norway. So some of the technology development perhaps is to create a safer working place. This is a common ring today. Common tasks and operations are feeding, observation, taking care of the dead fish, cleaning, maintenance. And there are, of course, safety challenges relating to that harsh environment, to the open environment. You can see the persons, they're not very large compared to the ring and the forces that where they work. But other safety challenges could have easily been taken away if we had more creative organizations. Because we have the safety challenges coming with that we often need to perform operations hastily and with few people, perhaps having long hours and few breaks, leading to injuries and strains in manual operations and in stressful work that actually didn't have to be that stressful. So that will perhaps also be one reason to make more technology or automatize the operations. And we will hear more about the different solutions. That is what you know about and not me, the different solutions on how to avoid those manual operations. So we will hear more about that later on. So, but are we able to make use of this technology, both the robotics, the large concept? Will it create safer workplaces? I'm not sure if you use the expression bob, but I couldn't find an emoji saying both yes and no, or So I'm not sure if, I think all of us believe that technology can create safer working places, but also we often get that negative side effect. This is an example of one of the new farming concepts that isn't started yet, but it's close to become a reality. You can see that people will be very small in this gigantic construction with a lot of fish. So in the new concepts, we can see that there are huge dimensions, a lot of fish, and those value and investments, a lot of energy and power forces related to it. So when we have been talking with people working at these kinds of concepts, or in some of the ones that are up and running, or developing the ones that haven't been started yet, we can see that some of the challenges will be related both to the, what we say in the safety research, in the sharp end, in the operations, but also in the offices. So you will have less manual routine operations, which increases the monitoring operations and also giving more complex operations out on the net pen, or what you call it, construction. I will say a little bit more about that. So the concepts do give more predictable daily tasks in control rooms. This is not directly dangerous, but it's still challenging for the health of the personnel. It's monotonous, staring at screens 24/7. It also requires experts in both fish biology and farming and practical things. And I'm not sure if those experts will want to have a control room working place. So it's challenging both ergonomically and psychosocially. Also, that could lead to strains, and it could lead to difficulties getting persons recruitment. A different story is the rarer operations out at sea, or where the fish is. When you move the fish or the construction, it's going to be, as I said, it's going to be large constructions, more advanced and complex constructions than what we have now with the ring. So it will demand much more people, different expertises, different organizations. They will have to do complex tasks together, like using cranes from vessels to braid mooring lines, or lifting these huge constructions that is below surface and high up in order to move fish or do maintenance. Many of the concepts also are, when they are underwater, they use ROVs, of course, outside between ropes and sensors. That's quite advanced. And some needs cleaning, lights and camera inside the net. And believe it or not, the common solution nowadays is to use divers, because ROVs aren't trusted inside the nets. So 20 meters and below, we use real life human divers. To wrap up, what we have seen is that the emerging concepts, they do on the safe side, they give stable working platforms, and they remove persons from the daily harsh conditions into the warm remote control rooms. but they also increase risk related to the inside rooms, to sit in front of screens. And in addition, it induces major accident potential due to the high energy operations involving many people and fish. So for some of these risks, robots are thought of, and they can save the day if they are implemented and developed in a good way. So remember what I told you in the start. When you create the robots or robotics, try to avoid the negative sides of the monitoring, for instance. If you can make the cooperation with the robots practical and healthy, it will also induce safety. Thank you.
Thank you very much, Christina. We will introduce then our next speaker, which unfortunately could not be here, but we have a video recording of his presentation. So please pay attention to that. And I would also like to hear during the beginning, if the people in the back, if you can hear the audio well enough, then we could tune that. So I will start the video.
Hello, everyone. My name is Andrew Bennett. I'm with the MIT Sea Grant program in Cambridge, Massachusetts, and I'm here to talk to you a bit about our strategy for offshore aquaculture. But first, what is a Sea Grant program? Sea Grant is a federal university partnership program that will bring science together with communities for solutions that work. It was established by the U.S. Congress in 1966 and works to create and maintain a healthy coastal environment and economy. It consists of partnerships between the National Oceanographic and Atmospheric Administration and 34 university-based programs. There is a Sea Grant in every coastal state, as well as Guam, Hawaii, and Puerto Rico. So each Sea Grant looks at its particular state. In our case, of course, that's Massachusetts. And Massachusetts has always been a seafood state. We currently are running $550 to $850 million per year of catches. The single most popular port in terms of dollar value of catch is New Bedford, Massachusetts. We may not be the largest in pounds caught, but we are number one in the country on seafood value caught. It is seafood has always been a backbone of the state's economy. It's always been integral to the culture of Massachusetts. Indeed, the oldest non-indigenous fishing port dating back to the 1600s is Gloucester, Massachusetts. And we have always enjoyed a strong legislative support to maintain our fisheries industry and our seafood industry. And we have a diverse range of constituents, different ethnic groups, different backgrounds, all contributing to our marine economy. Now, what does Sea Grant actually do? Well, we do a lot. We have three primary thrusts: research, outreach, and education, and that manifests in a lot of ways. And you can see this is a pretty busy eye chart here. We do design of aquaculture equipment. We do automation, resilience, ecosystem interactions. We study ocean acidification. We're doing an awful lot of work, but what matters here is these particular ones. I'm looking at farm management robotics, AI and machine learning for fisheries management, ocean acidification impact on shell formation, which has an effect on the scallop and the oyster industries here. For monitoring, we have an autonomous sailboat program. We have an autonomous profiler, which I will talk to you in just a moment about. We also look at other issues like the eelgrass aquaculture co-location, which is legislated in the state. And we have a project in disaster preparedness for oil spills in aquaculture. What happens in the event of a calamity? What do we do to protect the aquaculture industry? All of this is driven by our strategic plan. The National Sea Grant Program has strategic goals they want met, and our plan is designed to achieve those goals. In particular, in this case, number 3, developing technologies that will be transferred to the coastal resource industries so they can employ technologies and reinforce strategies to ensure safe and sustainable seafood and products. So the whole point is get this out there in the hands of our communities of stakeholders. So the first project I'll talk about is Zippy. Zippy is a coastal monitoring robot. The problem here is when you want to do coastal monitoring, especially over a long period of time, You want to do it to help local communities plan for the future and provide insight into what sustainable practices are working and what are the effects. How is changes along the coastline affecting coastal industries? Collecting this kind of data can be difficult, it can be costly and quite dangerous in the event of, well, we've had 2 hurricanes in Florida so far this year that have been pretty significant in the impact to the coast. So we want to build something that we can deploy to get the data we want without being swept away or destroyed by the systems. So we have an autonomous vehicle in this case. We designed it for in situ dynamic data collection. So what does that mean? It is a cable-mounted robotic vehicle. It has a simple controller aboard that controls the position through motor and drivetrain. It has sensors for data logging of the health of the robot, the position of the robot along the cable, the depth of the water that it's in, and it will carry any one of a variety of sensors. Really, we're just limited by the weight of the payload you want to bring. In the case of this particular test, the picture you see on the right, it was an Aquatrol 600, which we used for this deployment to collect things like pH levels and oxygen, turbidity, temperature, depth, things like that. So there we go. Here's a sample of Zippy doing its thing. The point of Zippy is to be low cost so that local businesses can afford to have one around, or local towns can afford to mount one. It is autonomous. It will carry any sensor you might want. And there are a variety of ways you can install Zippy. You could have it running vertically through the water column. You could install it like in the lower left image. Perhaps you have a river you want to monitor at certain times. Zippy can dip in and out of the river on a regular basis. Perhaps you have an area where you want to do a traverse. So you have both spatial and temporal. That's like the middle image where we can, say, traverse an aquafarm or someplace like that to collect data both spatially and through time. You can have it mounted as originally intended with one end in the ocean and one end on shore. And now Zippy runs in and out regardless of the tide, regardless of the waves, regardless of the weather, and will collect data for you. So lots of installation options. Installation and removal is quick and easy. There are some fasteners on the side. You can clamp it to the cable and turn it loose. And it will happily collect anything you want to know about the water column. So here's a sample of one of our first long-term deployments. We sent it out for a week, running up and down the water column. We learned a lot, good news and bad news. The good news is we were getting lots of good traverses. We ran once an hour for 7 days. You can see in some of the data around August 14, 15, the robot got stuck at the bottom of the cable. We have since debugged it and figured it out what happened there, but happily it continued to collect data, just not along the cable like we'd intended. And then by the 17th, it had righted itself and it was happily running again and collecting the data that we were looking for. In this particular case, we're just comparing depth information to tidal information. So this one's a little more interesting because we have pH versus depth, which was of great interest to the aquafarm that we were located near because they had both scallops and oysters in the water and they wanted to know about shell formation. So we were giving them information about the pH levels as they varied with time and tide. It wasn't perfect, but since this was more of an endurance test of our prototype, we were happy we had any data at all. So we were kind of pleased about that. So what are we going to do now? Zippy proved out that it can work, but it had a few issues. So we built a new Zippy. This time, instead of using polymer, we used all stainless steel and aluminum. It is much tougher. The clamping force on the cable is much greater. We don't have slip issues like we did before. We can carry a significantly larger load, so we can now carry multiple sampling bottles if necessary. We want to add a little more to it. We want to improve the odometry, and we're going to be adding inductive charging to the system. So when it comes out of the water and docks, not only will it report its findings, but we will be able to inductively charge the batteries. This is a big deal because now you can deploy this indefinitely at some location. It could just be running traverses anywhere you want, as often as you want. And since it's inductive charging, we could do the entire thing underwater and leave the robot submerged for really any length of time. So that's Zippy. Our other major project right now is the oyster moran. This was brought about because we have insufficient staff to maintain oyster bags during growing season. MIT is a little different, or I should say Massachusetts is a little different in that local aquafarms are permitted on a town-by-town basis, which means that you have a lot of smaller operations going on, not great big operations. This limits the economic benefits and the economic leverage that a given oyster farm has. So costs are really, really important to them. Staffing is really, really important to them. It's tough to get staff in some of these locations. So they were asking for some automation to help them out. Flipping oyster baskets, as you can see in the lower right, is currently done manually with somebody in a kayak going out. You have to flip the basket about every 10 days because of biofouling that grows on the underside, and that will choke off the water flow to the oysters. So you flip the bag, and that allows the biofouling to dry out and die off on the top side, while the bottom side is exposed to the water and the oysters continue to feed. And then you just repeat this throughout the season. The bags will start fairly lightweight, but by the end of the season, you can get up to 30 kilograms per bag. There's a good chance for shoulder and back injuries because you're not really having great leverage when you're sitting in a kayak doing this. Also, you have to do it in all weather, which tends to not be great fun for the oyster employees, aquafarm employees. So we built Aquamoran here, Oyster Moran. Oyster Moran's job is to flip the baskets autonomously. We have it autonomously recognizing bags, recognizing fields of bags, and maneuvering into the bag field to flip the bags. So we've now worked on to Gen 2. So our Gen 1 robot was a great learning lesson. We gave it some thrusters, we gave it a flipping mechanism. Some of the things we discovered was the baskets, when they're being forced by tidal flow, press together, they press against the boat. So we needed to give the boat the ability to wiggle itself free, to struggle, if you will, and get free of the baskets. So we gave it additional thrusters in the bow. We also improved the autonomous basket recognition. Early on, we were using fiducials. Now we don't need that. We'll just know a basket when we see one. And we've changed out the flipping mechanism. The first one worked okay, but it didn't shake the basket. After you flip the basket, the oysters tend to all roll to one side. So you've got to actually give it a bit of a shake to get the baskets to level out the oysters, which is better for the oysters for their growth rate. Besides going back to maneuvering, besides adding the lateral thrusters originally to wiggle the boat, we discovered that the thrusters also work really well to kind of push the baskets apart to ease the maneuvering. So we were kind of happy about that. And in general, it's working really well. And you see our latest generation in the bottom right. This was an early field test, and we're going out for an extended deployment this fall. And that's all I've got right now. We're working on other projects involving upwellers and similar systems. More autonomy in the oyster seed industry, but we don't really have a lot to show yet, so I hope to have more for you another time. Thank you again.
Dr. Bennett is actually with us on the Teams, so he'll join the panel discussion later. Thank you for a very interesting talk. And this is like a classic example of a typical aquaculture operation. This guy in the canoe flipping these heavy cages. And then we have some robotic solution that can assist in that. Our next speaker is stepping in on short notice. Thank you for that, Leanne. So give it up for Leanne Thompson. Find your presentation. This one, right? Yep.
Hello, everybody.
Yep. There you go.
I know it's hard after lunch, right? So I am Leanna Thompson. I'm the CEO of Aquai Corporation, founded in Silicon Valley, California, where it's my hometown, home location. I'm also the CEO of Aquai Norway AS, which is located in Kvaløy in the north of Norway, in the edge of the Arctic Circle. And I'm also the CEO of Aquai MENA here in the fabulous UAE, where we've recently established a subsidiary and are busily making inroads and doing different work cases with our robotic fish. So today I'm going to talk to you about biomimicry and robotics and the importance of that. So Aquai isn't necessarily just focused on aquaculture. So when we built Aquai, or I should say my partner, Simeon Peter Koski, decided to make an affordable robot to monitor the waterways, it was really about addressing critical issues that are found in aquatic environments, in aquatic ecosystems, one of which is indeed aquaculture. So when he looked, so my little bit of background, my partner is 38 years in climate, 35 years in robotics, biomimic, humanoid robots, and now the robotic fish. So in looking what was out there in the waterways, we realized quickly that most of the units out in the waterways were built for the deep pockets of defense and, need I say, oil and gas. And a lot of those individuals, and obviously we see educational institutions, also have significant deep pockets to be building new technologies that most of the time then get picked up through those organizations that are able to actually have, who have those deep pockets to afford them. So we wanted to do something completely different. In true startup mentality, we wanted to make a system that everybody could afford. And that meant the fish farmer. That meant the conservationists. That meant the people who didn't have those deep pockets. And that led us to Aquai. There we go. So in improving sustainability in aquaculture, so the reason why we actually ended up in aquaculture was because in typical Silicon Valley form, the question is, great, build it. Prove you can build it first. And then after you build it, the next question is, okay, great, well, who's going to pay for it now? And so for us, I actually at the time saw a film called Fish on Your Plate. It was about one fish farm in the north of Norway who is doing the utmost sustainable efforts to create sustainable aquaculture. And in watching that, I thought to myself, robot fish to monitor live fish, that actually makes sense. So when I approached a farm up in the north of Norway, and they're called Kvare, I'm probably the Norwegians in the room, sorry, I'm trying. Kvare, how's that? And they supply Whole Foods and Michelin chefs and whatnot. And so I sent a 30-second clip of our robot, and they said, come. And the reason was is because it's really about dedicating, how can we improve aquaculture? How can we improve the industry, which is the lowest carbon footprint for providing protein, which is also the fastest growing ag sector today? But it's not enough to grow fast. It's not enough to feed a planet who has this insatiable hunger for seafood. We really need to have a sustainable system. And so it's really about how can we change aquaculture, learn from some bad players in the past, and have sustainability within aquaculture. And I think, again, it's about affordability. Yeah, it's not enough to have this amazing software. It's about having affordability so the systems you see in Norway could also be adopted to farms in Chile or in Asia or in Africa or different places, right? So it's really about affordability within that technology. And when I say software focus is not enough, I mean, there's some really cool stuff going on with software tools out there today, especially in aquaculture with machine learning and biomass predictions and lice detections and then the zapper. But all at the end of the day, they're still reliant on these static buoys and cameras that sometimes cost tens, if not hundreds of thousands of dollars. And then the problem with those static buoys and cameras is that they kind of remain in one place, hence the reason that they're called static. And you're really waiting for the stock to come to you in the case of aquaculture. So this is one of the reasons why I believe that having these expensive static systems and even these expensive software that goes with those expensive static systems is not scalable. Again, you have farms globally that, and while it is very expensive to send a diver in the north of Norway, I think last I asked it was maybe $10,000 an hour, $10,000. That is not the case in other parts of the world. And again, it gets back to the affordability. It gets back to not having super expensive systems, as great as they are. If we're really going to talk about sustainable aquaculture, we're really going to talk about impactful aquaculture to feed our growing planet and food security, then we also have to be focused on water security as well and cost. Thank you.
Maybe you have to use the arrows.
This one? This one? Still not moving. Excuse us. I have that effect on technology.
Yeah, so now you can use the arrows to move so this one advances.
And you might wait here, because when the video plays, because I can't see, you can hit it. So this one?
Yep.
Okay, so 1 second. So portability is where I left off, I believe, right? Portability is found in robotics, and you will learn as you see, and maybe even walking around here, and as robotics, this is the robotics era, through biomimicry, bio-inspired, whether it's a bird looking, a bee, spider crawling, clamp, you name it. It's all about biomimicry. And so this is what we focused on, is about how could we use bio-inspired robotics to actually make aquaculture more affordable, but also more optimized so that the farmers are still getting the metrics that they need, the visuals that they need to make the decisions that they need to make. Here. And I'm going to give you an example here. You can hit that arrow.
Yep.
Be great.
Okay, so it's playing.
Okay, cool. I'm going to give you an example of our robot. So we actually went to the north of Norway, as I left off in my story. And the first thing that we wanted to do was see how the salmon would react. Now, typically salmon, you know, they're prone to heart attack. They don't exactly like new devices in the cages. So the first test that we did in November was to just throw a unit in and see how the salmon reacted. And to all of our wonder, it was literally within minutes, maybe a half an hour, that the salmon were already comfortable swimming with our robotic fish. They embraced us like one of them. So we went on to do more tests, as I said, in more cages and farms, but also in dams and also with ducks and also in rivers and also in coastal lines. And here you're seeing some of the dashboard, some of the metrics, and I'll get more into the technical of the robot in a second. And then ultimately a success for us. We went from San Diego, we went to the farm. We actually then after that test moved to the farm for 2 months, really understanding the pain points of the aquaculture farmers. We brought 7, maybe 8 3D printers, the whole team. We moved on to the island of 60 people, 3D printed 8 robots in 6 weeks and deployed them. So my point is, again, affordability. So biomimicry in manufacturing helps with fewer screws and fewer links, which helps with maintenance and helps also with costs, keeps the cost down. My partner has 30 years in manufacturing robotics, but also 3D printing. So we use 3D or SLS printers for our technology, and that also keeps the cost down. So, is that one?
It's playing.
No, it already played. There we go.
There we go.
So getting back to biomimicry, a lot of the first questions we get from technologists or other customers, scientists, whatnot, is, well, why fish? Why can't it be like some of the boxes that we've seen today or so? Why a fish? Well, Mother Nature, 20 million years, she got it right, or he. And the idea is, again, the biomimetic system is power efficient because we use the undulation of the tail, which helps us with being power efficient and saves on battery power. We're also able to maneuver in very tight spaces because of the quick turn of the tail. And also, we immerse with the natural habitat, as I mentioned. So being able to immerse so nicely doesn't scare the stock, doesn't scare any ecosystem. You know, in fact, I think it was the Smithsonian asked us to swim with grouper because grouper are very skittish fish, and they wanted to be able to see the grouper spawning. So it's about using biomimicry. So why would you put a box in when you could put a fish in, right? We also, the tail is made out of neoprene, so it's very flexible and it can stand the rough seas of the north of Norway. I can deploy one in less than 5 minutes and 25 knot winds myself. Just to get back a little bit more onto the technology, because it is IROS, right? The actual vehicle does carry a payload of up to 16 different sensors. The usual payload in aquaculture is salinity, dissolved oxygen, temperature, depth, pH, of course. But we also have the option to put, it's a plug and play, built modular like Lego, other systems. It has cameras on board, 3 cameras, including a belly cam, a side scanner to do net inspections. And the other beautiful thing about having a biomimetic autonomous system in aquaculture is that you can go to different depths. So let's say you need a reading at 3 or 6 or 9 meters. You can go to all those depths and you don't have to take your static camera up and down or sensors up and down. The robot just goes up and down on its own and it relays the information. In terms of the battery power, we ideally like you can swim up to 8 hours. You recharge usually every 4 to keep going. And again, it inductive charges, stays in the water up to, we had the ones in Norway were there about 10 months at a time and we took them out and we can go longer. So even now, when we talk about the technology, obviously different waters here, it's much more salinity. So it probably won't last a whole year in the waters here. But the idea is to really make an ease of use system that stays in the water and does the job of monitoring 24/7. But it's not just about the robot. I know it's IROS, so I'm focusing a lot on the robot. This is one of our latest models. It's about the data as well. So the robot harnesses the information. So again, proximity to the source and data acquisition. Why have something in the center of a 120 circumference cage and your sensors are on one side and your fish are on another, and the sensors get great reading, you have an oxygen drop on the other side, and all of a sudden you have an issue to solve. By having all of those cameras and sensors on the mobile platform swimming alongside the stock at all times, you're always getting the accurate data. So precision to the source and data acquisition. Then you can take it in the back. Then you can use AI, machine learning. We use computer vision, obviously obstacle avoidance and whatnot on the driving side of things. But on the back end, you apply those tools for predictive analytics. And then the customer, in our case, just logs onto a web dashboard. It's a SaaS model we call FAS. Fish as a service. So it's an end-to-end solution. A platform that's affordable that we lease, we do not sell. And that means that if there's problems or issues or upgrades, it's plug and play, booms, like I said, snap it out, snap it on. We are getting the data, we're pushing the data, which is raw data, or with the analytics to the customer. So again, the idea of having a cost effective system means scalability in aquaculture, bringing a solution that can be scalable, that doesn't require all the wires and 3 people and 3 days to dismantle the wiring, to clean the nets because they've gotten dirty, but to be able to throw it in and out of the water simply, tetherless, which is what's really going to transform the future of aquaculture, is affordability, is autonomy, the integration of autonomous systems, robotics, right? And then obviously the data, the precision data with it. So that's Aqua AI. And again, Liana, reach out to me if you have any questions or whatnot. I'm living here in Abu Dhabi now, so really happy to start integrating in the fish farms here and other use cases as well, from looking at ghost gear to monitoring our waterways, especially post-flooding. So thank you so much.
Thank you very much, Liana. So fun to see how this robot fish just immediately integrates with the real live fish. So we have reached the final presentation of this first session of invited speakers. And our speaker now is Dr. Nikos Papandreoulas from HCMR in Greece. So please welcome to the stage.
Not sure about how well this one is working, but
I had to
let's
play it from here some videos.
okay. So when you go to presenter mode, it goes up there, and then if you need to play, I guess you need to exit and then I'll find.
Good afternoon. I would like to thank the organizers for inviting me in this interesting meeting. Nikos Papandreoulas, I'm coming from Greece, from the Hellenic Center of Marine Research, and I'm going to present you some of the needs and the technological solutions that we have in the Mediterranean. Aquaculture is not only in Norway, Chile, but it also exists in other parts of the world. No, I'm gonna play from
Yeah, that's the folder where your videos
it.
are.
Okay, show me the key.
Yeah,
the
so
keys.
just use the right key to go advance the slides.
Neither this one.
Second.
Okay.
Now it should work.
Okay, before continuing, I want to present you a little bit the situation in the Mediterranean. Mediterranean aquaculture is focusing in two species, which is the sea bass and the sea bream, represent a total production of something like 600,000 metric tons in 2023, and actually presenting a decrease of about 5% since 2022. You see the distribution of different countries that are producing these two species. They are all over the Mediterranean. And if we dig a little bit more on the data, then we see that there are more countries involved, and not only more countries, but also more species. So if we want to have an overview on the characteristics of the sector, we can say that the Mediterranean sector is characterized by a species variety, which makes a huge difference than the Norway or the Chile. And these species have different feeding requirements, different behaviors, different tolerant limits to temperature, different disease resistance, and so many other differences that makes the situation a lot of complicated. But the majority of the species are found in sea cages. The major one at least, the bass, the bream, the migrant, the pagrus. And also in the Mediterranean, we have the tuna farming, which is a completely different story, and I'm not going to refer at all because it's different farming operation from the beginning to the end. And in the sea cages, most of the husbandry relies heavily on manual labor. And in the Mediterranean, we have small farms, and this is a clear indication of the fragmentation of the sector. And also we have a very varying regulatory framework in the sense that we have at least 12 countries involved. 3 of them are outside the European Union. Therefore, it's quite difficult to employ universally applied methods. We cannot transfer directly what's happening in other parts of the world. And it's very hard to create one species fits all algorithms if we come to this. Speaking about the needs of the sector, I'm going to start a little bit about the strategy. Who is defining the strategy of the sector? It's the European Union with a strategic document that defines the development of aquaculture. But it's also the General Council for Fisheries in the Mediterranean, which is of the Food and Agriculture Organization of the United Nations, which has a very strong role, particularly in the Mediterranean, in the Black Sea, and the countries outside of the EU. And in all the documents that you can find, if you can read, you can find always this data-driven knowledge-based farming, which is drive us to the future, and some words from the actual strategies that we need to leverage innovation, digitalization, knowledge base. We need to have effective spatial planning, embracing digitalization and innovation. And of course, that always technology has a key role, reliable, and we need reliable data for this. And if I can summarize the short-term technological needs of the sector, I would say that we need to monitor the environment, and this is of particular importance because of the climate change and the impact of the climate change in the region, which is a hotspot of climate change. We need to develop artificially intelligence-driven feeding systems, and we need always a better management, fish health and welfare, and of course we have to monitor and be sure about the safety of the infrastructure and the employees. And I'm going to present you some examples of what we are doing. There are several groups that are active in technology development currently in the Med and in the institution around. All are working in the frame of European or national projects. And I'm giving you here a list, which is obviously not complete, of the different projects that are active or has been implementing technological solutions in the Mediterranean. And as I said, in the 4 topics that I mentioned before as high priorities, I'm going to give you some examples of what's going on. And I'm going to start with the environmental monitoring. There are several companies now that are active in the region, from France, Denmark, even Greece, that they provide platforms for online monitoring of the environment with real-time data management, and also giving the possibility of some predictive modeling that give us the opportunity to predict somehow some parameters in the future. But all these, let's say, platforms give us the chance to monitor a farm, either by having different sensors within the cages or around the cages or in an area around of a farm. But it's getting more and more important to monitor several farms, wider areas where we have here, for example, in this picture that I'm showing you, there are 7 farms collocated in a quite close area. So we need to understand the interactions and how the environment is affecting not only one farm, but all around. And for this, we need a little bit different, a different approach, let's say, not only sensors, but we need different type of data, like satellite images. And in the European Union, we have the Copernicus system, which give us this possibility. They provide us with data that allow us to monitor wider areas. And in this example that I'm showing you here, we have the information for the temperature and the chlorophyll, which is the presence of phytoplankton, nanoparticles in the water. And then with an algorithm, we have been able to estimate the oxygen concentration in wider areas, and this give us the chance to have a better overview of what's going on in a wider farm. Of course, there is a platform, a web-based platform always there, where we collect the data, and with the help of biological models that provide us with information about the requirements of the species in the future, in 1 week, let's say, for the oxygen demand, for example, we are able to monitor better the farm and also to apply improved husbandry practices, and the farmers can really manage their farm in a better way. Feeding control. Why this is important? We all know feed represents one of the biggest part of the operational cost in the farm. We know that it's a multi-parametric problem. It depends on the environment, the physiology of the species, and also the behavior. And this is where we have been concentrating recently, having some, wanted to answer some questions like how fish behave during feeding, and if we can understand when the fish are satiated, when we can stop feeding, how we can control feeding in a better way. So we use cameras, static cameras, but we hope that we are going to use something different in the future. And we have a pilot farm where we are able to do trials, actually, and you see how the fish behave. We are able to track and detect the fish and take some information about their speed and their direction. And also we are able to monitor the specific activities that the fish have during feeding. And you see that the sea bass, for example, has this strange, high dense activity when they are fed, which is completely different than with other species. So we have to develop similar algorithms for all the species that we are interested for. Oh, come on now. So gathering all this information, we are able to take out an index, a feeding index, as we call it, which automatically clustered in 4 groups. The black one that you see here represents the behavior of a fish before feeding, when they anticipate feeding. The red and the gray ones are the actual feeding periods, when normal feeding occurs. And the blue one represents the relaxing post-feeding behavior. And what it is important, and we were very happy when we saw it, is that when we overfed the fish, when we provide for longer period food, then this post-feeding behavior appears, although we still provide feed to the individuals. And when we have reduced feeding, the graph below, this one, it shows that the feeding behavior is still expressed while there's no food available. And when there is no feeding at all, then the anticipated feeding behavior is expressed at the time when the fish are expecting the food to be available. So this gives us the possibility to control somehow the feeding. And I invite you to check also the poster session when my colleague Dimitra Georgopoulou will make a presentation on this. And there is also a poster where we can discuss more detail on how this came up. Now, apart from feeding, it is of particular interest that the monitoring of the fish in terms of their size and also on its welfare, on their welfare. And there are some operational welfare indicators that has been defined based on external parameters and external characteristics of the fish. So we use, in this particular case, a stereoscopic camera, where we define several morphometric characters on the fish. And then we are able to see not only the size of the individuals, but also the presence or not of external changes in their body, like color changes, lesions, fin erosions, and so on. And we have a quite good idea of the actual situation of our stock. Finally, I'm going to speak a little bit about cage net inspection, something that we are going to listen and much more later on. I don't need to say that this is a manual operation now, and the need why it is important to have an autonomous vehicle to do this operation. So, some years ago, we have been working in this direction and trying to have a real-time navigation with target recognition. We used a blue of small robot, and you see how we have been testing it again in our cages with several thousand of individuals of bream, and we have been successfully make the rope complete the navigation and monitor the fish while having on board also particular algorithms that were able to monitor the integrity of the net and whether or not there are holes or other disturbances in there. Speaking about cage net inspection, I would like to mention two more much more recent projects. One is the Calypso autonomous underwater vehicle that came from a Greek group from the University of Aegean that they have developed from scratch a new AUV, and they have also attached an arm on it, so in order to make some manipulation. And also the Hector project that we are going to hear much more later today in the next session that came from the Croatian group. And to close a little bit this summary of what's going on in the Mediterranean, I'm going to show you some of the future challenges of the sector. And I'm going to start with climate change because this is of particular importance because it affects all the production chain of the industry, the fish, the infrastructure, the personnel, everybody. So we have to focus on this. We need to find new farming areas, and the sector should decide whether or not they're going to move a little bit offshore or they are going to invest in RAS. And it's obvious that we have to, sorry, to take care about the sustainability of the sector in terms of environment, social and economic sustainability. If I have to give some lines of where to look for, I would say that we need data of various forms to perform some predictive modeling and to develop digital tools that are very important and essential for the sector. To apply the principles of precision fish farming, because this is going to transform absolutely the farming operation, not only in terms of improved decision making, but also for operational efficiency. And if I'm allowed to, in the notice like this, to provide some requirements from the sector, I would say that the use of autonomous vehicles for inspection and repairing of the nets is of particular importance. Also, before closing, I would like to give some attention to the skills and capacity building, because it's important of how this technology will pass to the sector, in fact, and we need to acquire knowledge with new approaches, with a multidisciplinary and transdisciplinary approach, and with novel mechanisms. Thank you for your attention. And if you have questions during the discussion afterwards, we are going to have this opportunity.
Thank you very much to all presenters in the first session. We are now moving into the poster presentations. So in just a couple of minutes, we will have our first poster presentation. And these will last for approximately 30 minutes before we have the panel discussion. So I would like to invite the presenter of the first poster. He is on video. Yes, all right. So unfortunately, this person could not make it. So let me start the video.
Hello everyone, I'm Matej, and in these next 3 minutes I'll try to get you interested in research that my colleagues and I have done on the topic of biofouling estimation of fish cages by filming the nets from the outside with an ROV. So, at the beginning of our project, we reached out to a local Croatian fish farming company with farms located at several locations in the Adriatic Sea. We visited one of their locations twice during summer months to capture underwater footage of their cages at different stages of accumulated biofouling, meaning that some of the filmed nets were freshly cleaned and some needed cleaning. They were also kind enough to provide us with an actual net to be used for testing. When the data was gathered, we developed proprietary annotation software that you can see in action here that let us annotate a few thousand images of the nets in an acceptable amount of time without the need to outsource the annotation, so that we could control the quality of it a bit more easily. The classes for the annotation were chosen to be sea, cage, fish, and blur. The annotated images were then used to train a UNet-based AI model for real-time semantic segmentation capability. After we knew what was what in the images, we created an algorithm to reverse engineer how a completely clean net should look like and compare that to the actual state of it. So the final output of our estimation algorithm is a number telling us how much biofouling is accumulated on the net from a 0 to 100. We also developed a closed-loop control algorithm for an ROV retrofitted with an underwater localization system that was used to capture footage of the provided net autonomously. An experiment where we knew exactly how much of the area of the net is covered in simulated biofouling was repeated several times, and the biofouling estimation was off by only 2.5% on average, which is more than precise enough to determine if a cage should be cleaned. Currently, divers perform visual inspections and subjectively decide whether to schedule the cleaning or not. Thank you to the organizers for the opportunity to present at this workshop, and thank you all for your attention. Hopefully, if there are any questions, we can answer them now online.
Thank you. And just to mention that all of the poster presentations, they will also have a poster in the poster area, which is over in the other end of this this building, in the break. Where did my mouse go? There it is. So then we will have a presentation here in on the stage from Atif Sultan on active vision-based real-time aquaculture net pen inspection using ROV. There you go.
Thank you very much. My name is Atif Sultan and I'm a PhD student at Khalifa University here in Abu Dhabi. So the research that we'll be discussing with you today is active vision-based real-time aquaculture net pens inspection using an ROV. So my research team is Dr. Wasim, Dr. Lakman, and Dr. Irfan Hussain, and we are part of Khalifa University Center for Autonomous Robotics over here in Abu Dhabi. Okay, the preamble for this research is to help the ROVs in better detecting the defects in aquaculture net pen. The idea is the aquaculture net pens have different defects such as hose or debris, which can lead to loss of fish and loss of fortune. For that, previously we used to have divers. We used to go there. Nowadays, because of increased safety and efficiency, we introduce ROVs over there. So the ROVs go there and detect using computer vision algorithm different defects in the net. So our idea is to add a layer of autonomy to this detection process by introducing a gradient estimation, which would help the robot to adjust its position with respect to the net. So this is the architecture main idea of our research. So going from left to right, so this is the net pen. The image is acquired by the ROV, and this gradient estimator is at heart of our research. The gradient estimator first extracts the gradient of the net from the image. It then matches this using a pre-trained model, which has been trained with images that are good distance, close distance, or far distance. Based on that, the gradient estimator tells the controller on the ROV that either you are near, far, or at a good distance from the net. So based on that, the controller commands the ROV to either move close or far from the net. And at the same time, the deep learning algorithms using the computer vision models are estimating different defects, either hole or debris in the net. And in real time, the ROV is being semi-autonomously controlled to move near or far from the net. Okay. So these are how close distance, good distance, and far distance images look like. And these are the results in actual aquaculture pen in Croatia. So you see here the gradient was far from being good. So the commands were given to the ROV to adjust its position. And according to that, if you can see gradually the ROV positions itself at an ideal distance from the net so that the computer vision algorithms can better detect the defects in that. So in this way, like at the moment, it can assist a remotely operated vehicle as well. And in future, if we have totally autonomous vehicles that are moving inside the water, it can really estimate, help them correct the final positions. Thank you.
Thank you very much. And we're moving quite quickly through the presentations. So next one is Wasim Akram, who will present about convolutional transformer for robust detection of aquaculture defects.
Hello everyone, thank you so much for being here. I'm Musli and I'm presenting or one of the paper convolution transformer for aquatic inspections. So basically, aquaculture, we are using fish farming in open sea environment, and they are uh, facing different challenges, and some of them are like net holes, biofouling, and aqua plants growth, and many more. And they require regular inspections. So the traditional way of inspection is using diver-based methods, which are dangerous for human life. So the alternative is robotic solutions. So the robotics and using the imaging data. So then computer vision and AI offers a great opportunity for performing the inspection task. So in this regard, we are proposing a novel method because the current traditional vision-based methods are insufficient or unable to perform very well because of the underwater environment and low visibility and many other challenges. And the traditional vision-based models are primarily designed for other environmental data. So that's why we are proposing a new novel transformer-based vision model for the inspection task. So the proposed model, this is the architecture diagram of the proposed model, and it contains different layers, uh, and these layers are identity, hierarchical, and preservations. So each layers perform their distinct activities and taking the input images and extract the features based on the annotations of different classes. So these are some of the segmentation results on different data sets. So we basically use different kind of data set. One is inherited from the Labo stream of the actual aqua farms for the biofouling classes. And this is another custom data set we have prepared in our lab environment, representing the aquatic plants and some kind of holes in the net present. So these figures show some of the segmentation of the plant growth on the net and as well as the net holes present in the net. So our results show some significant improvement over the current traditional computer vision models. And we have published this work in some of the reputed journals. That's all. Our poster are there in the poster area. So any questions we can discuss there. Thank you so much.
Thank you very much. Then we move on to the next presentation with the presenter here in the room. It's Dimitris Moskakis presenting on enhanced realistic tank environment. Here you go.
And you can try and use it. If it doesn't work, use the arrows. This is go. Yeah, okay. Yeah. But it's forward. Towards the computer.
Hello, my name is Dimitris Moskakis, and I'm a research fellow at the Norwegian University of Science and Technology. As well, it is well established, aquaculture plays a significant role in the economic global scale. It has experienced significant technology developments in the fish biology and the production environment, and several novel studies aim to improve the aquaculture practices and the fish welfare. Our objective with this project is to use non-invasive system to assess stress response in a salt group, to provide and enable a warning system that informs us about the state of the fish. Hence, we created a novel tank environment that can mimic the light conditions that exist on site. We implemented over there novel technologies. And as a sentence, we can say that we are using the fish as sensors. So as you can see here, we have developed an enhanced tank environment that we have used a submersible LED light that can homogeneously illuminate the tank, where the light scale is similar to the daylight. So we can adjust this light support frame to the desired depth, so we can provide all the tank in a homogeneous way. Also, we have established and we have installed a camouflage frame where all the instruments, the sensors, the water inlets and outlets are, let's say, hidden behind this camouflage wall. So we have a clean arena for the fish. And through that, we avoid the fish collision and the potential impact of the presence of these external factors. So based on this sea cage replica, we have deployed some systems to estimate the behavioral analysis of the fish. We have put some visual cameras, so the monocular and the stereo camera, and also some novel technologies such as a sonar and an event camera that they all work as a combination to assess the behavioral analysis of the fish based on some external stress factors such as light intensity and temperature. As a conclusion, we can say that we have developed an enhanced tank environment that can mimic the sea light prevailing conditions that exist on site. We have used some novel technologies, novels, and the visual cameras. And our aim is to improve the quality of the final product and, of course, to ensure the ethical production practices. Thank you for your time. And if you have any questions, I would be glad to discuss the poster section. Thank you.
Thank you very much, Dimitris. Then we're moving on to presentation by Lynn Erimo on biology and technology interaction. There you go.
Thank you. My name is Linda Nilsson Erimo, and I'm a research scientist at Fisheries and Aquaculture. And I'm here to present some experiments we've done trying to see how robots affect fish in the Norwegian farming of salmon. And this is work that I've done with my colleagues at Fisheries and Aquaculture and NTNU. This work is also part of a larger project called Change, an underwater robotics concept for dynamically changing environments, where MIT and NTNU is also involved. So by now, we've heard many of the other presenters talk about how aquaculture industry, especially in Norway, can be very challenging. It's dangerous can be dangerous for the people involved because of weather conditions. And it's also a need to make it safer for the fish. And to do that, we can, of course, use technology. We can use robots. There are many solutions that already are here. We don't know enough about how this technology actually impacts the fish. So we tried to do some experiments where we took a mid-size ROV and deployed it with sonars and a stereo camera. And then we did some movement tests that were very typical for both inspection and intervention operations. Put the thrusters on and off in high and low intensity, did some movements, and also did some turning movements to simulate an inspection. And here's the data. On the left here, you can see the sonar data showing the fish distribution around the robot. And using deep learning methods, we were able to quantify the distance that the fish would keep from the robot during the different tests. And in the same way, we use a stereo vision camera to quantify the distance the fish would keep to the camera. But this tells us something about how strongly the fish tries to avoid the robot. And we use the same stereo vision video to do a qualitative blind study where a series of reviewers watch these 5 seconds random videos of fish and try to score the level of escape response. What we saw that there were several cases where we got a strong reaction from the fish, especially during fast movements or high effect of the thrusters. And what we saw was that these 3 methods for analyzing the fish response to this technology, they gave similar results and showed And what we know now is that we should use these methods to do further trials to have an even larger data set to say something about how fish are reacting. react to the robot. Thank you.
Thank you very much. Then we have reached the last presentation of the poster session. And this one is also by someone who unfortunately could not attend, Dimitra Gergopoulou, and it's called Towards Precision Feeding Using Behavioral Monitoring in Marine Cages. So I will open this video and we'll enjoy this for the next couple of minutes. If there is no sound.
Hello, I'm Dimitra Georgopoulou, and today I will present to you a tool we have developed for monitoring the fish behavior in marine cages. In aquaculture, feeding is one of the primary factors that can significantly affect the farm costs, the fish welfare, and the surrounding environment. For this reason, it is very important to prioritize and optimize feeding. We know from research that the satiation levels are tightly linked to specific behavioral responses in fish, and therefore we can optimize feeding by monitoring the behavior of the fish. Here we had a double aim. First, to develop a tool that can constantly monitor the behavior of the fish in marine cages, and second, we wanted to identify indicators for detecting satiation levels in European seabass. For this, we planned an experiment where we fed the fish with different quantities, and during this period we were monitoring the changes in behavior using the submerged camera in our pilot scale farm. We used well-developed tools such as YOLO and DeepSort for detecting and tracking the fish. We corrected the camera for camera distortions, and because we were in a very mobile environment in the sea, we corrected for camera motion. From there, we extracted one of the behavioral parameters tested, the speed, but also using other computer vision techniques, we extracted the feeding behavior index that can show us the crowding level of the group. From the analysis, I will present two basic results, one for each parameter. For the speed, we can observe three things: that there must be a threshold of speed values over which there is an increased activity related to feeding. Second, that we see that there are differences in the duration of the excitation depending on the feeding quantity. And last, that we see that there are differences in the activity patterns. There is a symmetric behavior relative to the start of the feeding during normal quantities, and then asymmetry in the other scenarios. For the feeding behavior index, we automatically grouped the time series data into 4 clusters of behavior: the pre-feeding cluster in black, the 2 feeding clusters in red and gray, and the post-feeding cluster in blue. We saw differences in the clustering for different scenarios, where the post-feeding cluster in overfeeding scenario appeared before the feeding ended, indicating earlier satiation. The opposite was observed in reduced feeding, and also for the no feeding scenario, we saw that the pre-feeding cluster appeared also after the expected feeding time. To conclude, both parameters could be used as indicators and could help achieving precision feeding. With this, I would like to thank you for listening, and if you need more information, you can check our published paper or send me an email. Thank you.
So, thank you to the poster presenters. We are moving on in the program to the panel discussion. So, I would like to invite the panel participants, which are the presenters from session 1, back to the stage, please. And we have Nikos Papadrakis, Christina Sturgeon, Diana Thompson, and we will also get Andrew Bennett through the online service. So I will try and set that up now. So, Andrew, I think that you are.
Can you hear me?
I can hear you, and I think if I stop sharing my screen, and then I bring you over here. So, Andrew, you're currently the people in the room. They can see you. You can see them, but you're on the big screen now. And I think I'll then leave the microphone to the moderator of the panel discussion, which is Dr. Eleni Khalifa. There you go.
Okay, thank you so much. This is the last part of this workshop before the break. And I really want to thank everybody for the really inspiring presentations. And now I would like just to have a few discussions because we didn't have questions during this invited presentation. So first I will just try to ask a few questions and please enter the discussion so we can see and challenge them to see what are the solutions that the scientific community can provide for the challenges that aquaculture is facing. I would like to start in a sequence a bit small. First question to you, Christina. You said that Norway has been pioneer on adapting technologies and automated feeding systems and developing these new concepts for farming and stuff like that. And there is still a lot of risk and several of operations are done with the divers. So how do you see the farmers' opinion on putting robots on their facilities and how much trust they see on it? And if there are any regulations that are preventing them to use these systems?
Thank you. So to start with the first question regarding regulations, some regulations are there, for instance, when it comes to inspecting and collecting dead fish and that, but usually you get dispensation or you can use robotic if you have good documentation for fish welfare and that it's doable. When it comes to, because as I understood your question, it was about the willingness of the fish farmers in adapting new technologies.
Yes.
I would say that they are often quite traditional and think that it's enough to do already and that they can get profit and do the job as they used to. So conservatism perhaps is dominating, although I did show a lot of new concepts and innovations. And of course, most of the fish farmers would like to adapt new things if they know it works, but they don't want hustle and things getting into the way.
Thank you, Christina. Andrew, just to follow up on this, how's the situation in US since the sea grant has really connection with several farmers? Like you showed some robotic systems. Are they ready to use the systems or similar systems that you have presented, the farming or other aquaculture industries?
Was that directed at me? Sorry.
Yeah, the question is for you. Sorry.
The farmers are enthusiastic about adopting the technology as long as it makes economic sense.
Okay, and have you tested your systems in the farm? How they see the testing of them?
Yes, we have tested them in the field. There's a few aqua farms that let us come out and test on a regular basis. And it's been extremely helpful because there are always little things you don't think about that interfere with the operation of the robot. Deployment and recovery. We've discovered that the geometry of the baskets interfered with the geometry of the robot in the first generation. So we had to design a new hull geometry to compensate. We never would have caught that in modeling. It wasn't until we were actually in the ocean working with the baskets that we realized we had this issue.
Oh, thank you so much. And Liana, thank you so much for coming and the inspiring presentation. I really like your concept where you say we need to have affordable solutions for different countries and different regions and people with the coast and all the factors in order to have sustainable aquaculture. And I saw that you have already the system. You see, talk about data. What would, if you're in a robotic conference, there are like 3,000 researchers doing robotics and automation. So how would you see that our community help your system to be robust in order to be sustainable for the aquaculture industry?
So I'm not going to even pretend that I'm a scientist. And I won't tell you that we have an anti-MIT policy at our company either. Just kidding. We are technologists. We don't even come from the industry, but a lot of disruptors of industries don't come from the industry per se. To answer your question, so, I hire, as the CEO of the company, our team is made up of really unique Mad Hatters. People who are putting things on the Mars rover right now, people who are just, garage tinkerers, the Einsteins, this type of mindset. We haven't opted to work with institutions in the US, mostly because in the US especially, there's always, whenever you're working with institutions, they want to have control the IP, and then there's publications and all this, which is great, it has its place. But we opted to do a different route and just kind of build the technology, get it out there, get it tested, and like you were saying, looking at this big screen of you, it's just we learned so much in living with the farmers and really understood, originally when we went there, we didn't have a tether, then they wanted us to put a tether. And then we realized that that was a bad idea, but you do what your customer says, at least starting out. And then there was too much drag. It was problematic, especially you have all the lump sucker houses, you have all these other devices, the zappers going in there. So we ultimately removed the tether, and it was a huge learning curve. But I mean, we're always open to working with universities. I do have quite a bit of really remarkable interns that come from NTNU, we had in Norway, that we embrace that way. I would, as we grow, we're also very lean. I should point out, we have done most of all of this bootstrapped with just a little bit of investment from our corporate sponsor, Clare, and a couple of angel investors. So we just don't have the deep pockets of the institutions, but we're always happy to work with those, and as long as we get to keep our IP.
Thank you. I think we have excellent researchers here, and they are very eager to solve problems. So I hope we can define some of the challenges, and then we can challenge them so they can find some solutions to help. And we are, I think, more interested on publishing, but hopefully the collaboration of industry and research that can help a lot both. Thank you, Liana. Nico, I have one question for you. You presented the Mediterranean part. So we talked a lot about salmon and Norway, and we see that, we are using a lot of new technologies in Norway. And I would really like to see what is the status of the Mediterranean when we talk, like, are there already on the industry solutions? And how do you see this happening of the affordable solutions that Liana was talking?
You put all the questions together. So let's start slow. In the Mediterranean, the technology is not that developed as in Norway. The premium bus industry is lacking technological solutions compared to the south. And there are a couple of reasons. One is, as I mentioned, the fragmentation of the sector and the lack of a clear strategy of where they're going to go. This is critical. The second is that there's an economic issue. Speaking about affordability, this is very critical, especially for a sector that is facing economic issues, marketing issues, and so on. So they actually don't care about robots in their farms unless they solve the economic problem that they have. And then there is another issue. In south of Europe, there is neither a clear strategy from the universities and the institution to develop technological solutions for an industry like aquaculture. Because aquaculture is not considered as an important sector for the countries, not even for Greece, but represent the second product for export. So we have some difficulties of finding, not finding, but keeping and continue working with groups of people to develop further some ideas. I present this stupid robot thing that we have been working with something like 10 years ago. And there was, even though we have published more than 10 papers, there was no initiative either from any other institution or from the private sector to continue working with this. So we have all this problematic. And then we have an additional issue, which is the different species that we work with. And unfortunately, the technological solutions that are developed in other parts of the world are not directly applicable in the setup in the term. But I think that it's something that it's getting there because the problems are there. And they start realizing that we have no other way of solving the problem unless they go for technology, for new technology, a new solution. Business as usual is bringing problems. They lose money and they cannot continue like this.
Okay, thank you, Nikos. Are there any questions from the audience that you would like to discuss with our panel before we go for the break? Yes.
Thank you for our good presentations. And I want to ask, what kind of data was not available before using robotics, and what kind of data became available by using this robotics technology in this aquaculture? Only the cost problem, or was there some new data we could attain? Anyone?
I can just speak from obviously my perspective and hand the microphone over. So we actually, the data exists, the sensors exist. So for us, it was about taking the static sensors, the static cameras that, as I mentioned before, especially in where you saw the size of these cages, and they're typically on buoys or on a static pole. The cameras are in the middle of the pen. So what we did, we just took the same sensors and cameras and just put it on a mobile platform. So the data is virtually the same, but what they get is not just the same data, they get it right up close to the stock, especially when you have light variations. It's very problematic, even for those really expensive cameras. And then also, I mentioned in my talk about the shift in oxygen drops, but we're also giving the added benefit of doing net inspection, going to the bottom, seeing how much feed has been wasted. As you pointed out, feed is 50% the cost of the farmer. So if you can even do, decrease that 1%, you're saving the money. So just based on the cameras, like how sluggish the fish are swimming, that'll tell the HQ that why, turn off the auto feeders in the case of Norway, because they're not eating anyway, and you're wasting feed and you're polluting the water environment. So it was really about giving them what they have at a better price point, but with an added benefit of having more value add for these extras, but also at a fraction of the cost and also a fraction of the hassle.
Yeah, just to add up, I completely agree with what has been mentioned. There's not real question of data that are not available. And just the application of different ideas. And then what is missing from my point of view is how all these robots and all these machines that we put in a cage interact with the fish. And this is important, which is it's never going to be available any data unless you have the machine you put it there. And then you see how fish react, and then you adapt accordingly, developing further the machine and probably having solutions like the one the biomimicry is going to be solution. But we're going to listen afterwards much more in this.
Thank you. I'm not using the robotics or data myself, but I do know that in the concepts I presented, they get more data than before. They collect more data, but the general impression is that it's not good data still. It's not employed sufficiently still, but in the new farming concepts, it's much easier to get data from different kinds of both sensors and robots. It's going to be better soon again. Yes.
Do you have any comment before I keep this?
Our zipline robot was the first time they'd ever actually collected data. They had been using historical growth information about their, in this case, scallops and oysters. So they were very excited to get some spatial data and water quality. It caused them to change the locations that they were hanging the baskets.
Thank you so much. I think I just informed that we are running only 5 minutes late, which is not that bad if I say so. We have next session. It was planned for 55, right? But we can start exactly. So we can get from now 10 minutes break. And I would like to welcome you for the next session. And thank you so much for our invited speakers for the excellent comments. And we hope that we can help with all these challenges. Welcome back in 10 minutes.
Hello, welcome back to the second part of this workshop entitled Autonomous Robotic Systems in Aquaculture. In this part of the workshop, we're gonna have this second session where autonomous robotic solutions in academia will be presented, and there will be several invited talks talking about novel methods, dedicated robotic concept prototypes, and lessons learned, and it will follow with poster presentations and panel discussion before we close the workshop. So in this session, the first presentation, it goes on the underwater robotic solutions for autonomous IMR operations in fish farms. And I am Eleni Kelasidi, and I will give this presentation. Underwater robotic solutions for autonomous IMR operations in fish farms. And I will present mainly this type of solutions in aquaculture in Norway, where we will start with the motivation using such robotic system in aquaculture, discuss the challenges and current R&D and industry solutions before we move towards the vision how to utilize such system for sustainable aquaculture. Just the motivation, in Norway, aquaculture industry is one of the biggest industries, and from the starting point in 70s with these wooden structures towards this current industry standards with plastic floating structures, and the latest development, new development licenses where new concept has developed and deployed, there has been increasing interest and increasing the volume and the fish population, but this has not been the same on adapting new technologies. Only in Norway, now that there are about 1,000 farms around the coastline, and several of the operations are done manually, and there are risks associated with the personnel working in these facilities, fish welfare, preservation, and structural health. This indicates that there is a need for robust, safe, and efficient autonomous inspection, maintenance, and repair operation. Currently, the practice is the following in majority of the cases where there are several service vessels with cranes and people on board that they are performing in daily basis several operations in fish farms. But there are several fundamental challenges to growth related to fish welfare, mortality, escapees, sea lice, working conditions, and the industry needs new solutions. Therefore, the Norwegian government lately has asked the fish farmers to propose new solutions in order to target some of these challenges, as mentioned earlier from Christina.
But we know that new concepts might bring new challenges, right? And innovations might bring new risks. And as the researchers, we really need to develop solutions that should be robust, safe, and efficient when we are adapting robotic systems. In our group in SINTEF, we really use underwater robots and study them and develop them to use for aquaculture. And we're not the only ones start using robotic systems. There have been used in so many, and when oil and gas being a dominant industry using them. And the question that we always face is why you don't use these robots? And then you need a new one, and what is the problem? So robotic systems in aquaculture, they're facing completely different conditions because they operate on the wave zone. They are not anymore on the seabed that you will see robotic system in oil and gas, for instance. They are dealing with flexible structures. They are not anymore doing this on a rigid structures like pipelines, etc. And the biggest part difference here, what we're talking in several presentations we saw earlier, is that there is a biology component that we cannot forget because all these robots need to operate inside the cages, which has up to 200,000 fish. So we really need aquaculture dedicated solutions if we are going to develop technologies to be used in this industry. Therefore, we thought it's very important to establish the first aquaculture dedicated robotic system, lab, which will work both on basic research and also innovative solutions towards making such systems sustainable for aquaculture. But why and how many? So we needed to start from the beginning and see which operations are relevant to utilize robotic systems. And there is an enormous list. And we're starting now to see the most important, like the inspection of the nets, monitoring of the structures, of the environment, of the fish, and also some type of intervention repair, like cleaning the nets, etc. And in the group, the main goal is to do this autonomously because we have seen manual operations that happening. But to make them autonomous, we really need to develop novel methods, motion planning concept, target the perception of it, the communication, localization, all these parts that are the same in all the marine domains. But aquaculture is bringing the extra challenges that we have talked earlier that we need to incorporate, for instance, on the solutions we're going to develop. So we see that we can do this. I'm sorry, there is something on the slide. So we can see that there is a need with a lot of sensors, a lot of robots, and there are some on the marine industry, but we are trying to integrate all of them in the aquaculture and see how they can operate. So we need the multimodality of the sensors to localize these systems in order to target the autonomy. So we can build different versions of them and check which ones are the best to use. But to test them, we need an environment that's realistic. And we have the pleasure to operate our own facilities with 4 fish farms in Norway, where we can deploy all these systems and test. As mentioned earlier in the panel discussions, while testing in the really environment of the domain of the industry, they also realize what concept can be suited and which ones we should adapt, and we learn from them. So it's very nice to have there, but I want to show you that it's not like nothing happened when it comes to the robotics in aquaculture. There are a lot of solutions there, and we have several projects, both working together with the industry, but also very disruptive research when it comes to address some of the challenges. So we'll go on my presentation through 3 different concepts where I will show how robots can be used to monitor first the environment because they're interested to know what the temperature, oxygen, and all this on their farms that they're operating and growing their fish. They need to know if they have a hose, biofouling, and how the robotic system has been demonstrated for such inspection operation. And also, like, what is the status of the biomass? If that, because this is their profit. So how we can utilize robots to do that? Intervention is kind of a pain, and we all know about it, right? And intervention in aquaculture with flexible structures and 200,000 fish moving around, it's even more pain. So there are limited work has done when it comes to intervention, and we'll present some of the results now in Norway. So when it comes to inspection monitoring operation by using robotic systems, I want to show you this concept of the underwater vehicle that is utilized to do 24/7 inspection. And this is done in the fish farm that we have in Sinter. So we went out there, and since localization is a challenge, we need to, and we don't have a GPS underwater, so we have to deploy their locators in order to get positions from the different points of the net, and then being able to use numerical models in order to estimate the real-time destruction deformation. And by knowing this information and also having an acoustic sensor locator on the ROV, we will able also to know the position of the vehicle. By knowing now the relative, the vehicle will be able to autonomously 24/7 operate inside and start gathering 24/7 high quality data that we can use in order to obtain information about the status of the environment of the fish and the structure. So several sensors have been adapted, and we work very closely with the industries making both the sensors, the localization system, but also the fish farmers. So these are kind of the type of data we collected where we can get videos of the net, and then we can apply a simple FFT method in order to get the structure and what is the distance of the fish of the robot from the structure. And then we can see how good is the quality of the images we are using. We also can use this in order to get holes, identify the holes on the net. If we're able to gather all this information, so this is how it can work. And we have the flexibility in the sense that we're operating this, we can go there and hang in empty cage whole nets. So we don't want to have escapees, but we need to test this algorithm when we are doing this operation. When it comes to fish, if you are constantly recording, then you can able to use computer vision methods to identify them individually, count them, detect them, monitor their behavior, and also like track them. If you are able to track their behavior all the time, knowing their velocity, orientation, distance that you have from the robot, as Lynn showed, you can say something about their behavior change. And then we can see why the robots and what types should be used in aquaculture domain. But this previous video was perfect, but this is the reality that is the industry facing in most of the cases, right? And in bear, I cannot see with my eyes and identify any of the fish, but then by using technologies, we can identify both the fish and also the wounds that the fish has there, which is an important information for the fish farmer. We have several projects targeted. This was single operation. There are projects where we have like multiple vehicles. That you have the USV, you have flying robot that goes, get the safe areas, and then deploy the ROV in order to do inspections of the nets, inside, outside of this. So here we see full autonomous net relative navigation by using DVL. And then using the beams of this DVL, you can estimate the relative distance and the orientation. And this is something that has attracted the industry's attention to avoid having really experienced operators doing this in fish farms. This is when it comes to the monitoring and inspection. When it comes to intervention, net cleaning has been something that lately in Norway has done mainly with the robots. So but they're still using service companies with experienced operators, and this is how they're doing. So different methods to deal with the biofouling, and there are already many products, but maybe they are not affordable, as Liana mentioned earlier, for every different country. But in Norway, there are all these concepts that they're utilizing. And the last one that have developed is this 24/7 permanent resident vehicles that we are deploying. But to target their autonomy of this, for instance, crawling robots that disturbing constantly the surface of the net in order for the biofouling to not grow, you need to make them to do this fully autonomously. But how do you solve the docking of this system in flexible structures? How do you have the communication and all this? And these are the components that we have targeted on our projects. And these are now products that the industry are testing in their facilities in Norway. So my conclusion is here that even though we have tested several robots, we still need aquaculture dedicated solutions. And we see that it's very important that these robots, technologies, tools, anything we put there, they should coexist with the fish when they are operating in the fish farms. And what we did is that we went back and said, we want to know how the fish feels. So how the sound affect their behavior? Is the color affecting their behavior? Is the size? What are the components? So we deployed on the robot a lot of sensors. We gather the data, we analyze them, and then we can quantify the change of the behavior. And this can be really important information to the people producing these robotic systems. But what should be the criteria on developing systems for this industry? When it comes to autonomous navigation, we need to have collision-free operation. So this is demonstrated a concept in our fish farm where the ROV Argus, the big one, is moving, trying to collect data, and then suddenly another one enters its path. So it's autonomously adapts its motion, avoids it, and when there is no more obstacle, it continues doing the operation. So I will move on this, and we'll move on the last part due to the time constraints. It's what we need, it's resilience autonomy. And we partnered with NTNU, with several companies developing robotic systems in order to increase the resilience of robotic system in aquaculture. And to do that, we have collected a lot of data from the fish farm, and this is something that we're gonna release in few days, both having all the fish recordings from stereo and single camera, recordings from the sensors like acoustic sensors and echo sounders, anything that we have collected so the community can use all this data and study which solutions we should have in aquaculture. The next step that the group is targeting is actually remote operations because everything is done. It's moving in exposed, semi-exposed areas, and we can't go. So we really need to go and move towards remote operation. So we have our control room in Trondheim, and we are sending the signal there, and then we're demonstrating with all these models we have and the live streaming of the signals to demonstrate remote operations. To conclude, I just want to say, I believe that aquaculture needs solutions to target the challenges, and robotic systems can be very relevant to target several of them, and it can be used for inspection, monitoring, repair, anything you can imagine. But to have them doing this autonomously, these are still all the open questions, and it's very relevant for the research community here to understand, and especially the marine community to merge together and start targeting all these challenges with the motion planning, launch and recovery, docking stations, intervention tools that are dedicated for the different domains and all this stuff. And with that, I would like to say thank you. And I hope that we can contribute to make more sustainable the industry. Thank you.
Thank you, Elena, for that very rich presentation. I'm impressed. Now we will give the floor to Dr. Nadir Kapetanovic. Are you here, Nadir? Huh? I'm sorry.
Online?
Yes. Benno is giving the presentation and
So do we play the video or is it? Yep.
So we will hear from Dr. Nadir Kapitanovic about multi-robot system for operations in aquaculture. Dr. Nadir is a postdoc at the University of Zagreb, Croatia. Benung is giving us the video.
Quite soon. Yep.
Good afternoon. My name is Nadir Kapitanovic, and I'm a leading researcher at the University of Zagreb Faculty of Electrical Engineering and Computing. So the name of my lecture is Multi-Robot System for Operations in Aquaculture, and I'll try to convey part of our experience with the Hector project that had to do with autonomous inspection missions in aquaculture. So first, a bit about the overview of the presentation itself. I'll go through some of the details of the Hector project, then the mariculture use cases as a part of that project, and then go through the vehicles that were integrated in the scope of Hector. So remotely operated Blue Eye Pro ROV, the in-house developed autonomous surface vehicle catamaran Korkira, landing platform, tether management system, the ROV underwater localization system, and in the end, the developed biofouling estimation algorithm based on cameras. Of course, we did sea trials to collect the data and test our equipment and algorithms, so that will be shown in the end. So Hector stands as an acronym for Heterogeneous Autonomous Robotic System in Viticulture and Mariculture. It's a project from the European Regional Development Funded project with a total budget of just under 1 million euros. The project coordinator was our faculty, so Faculty of Electrical Engineering and Computing from Zagreb, with two research laboratories, LARIX and Labust, being involved. LARIX being the lab is researching the all-terrain mobile robots and flying drones, and Labust, my lab, being involved with maritime robotics in general. So the other project partners were the Faculty of Agronomy from Zagreb and also the Institute of Marine and Coastal Research from University of Dubrovnik. So why research in mariculture? I guess the whole workshop is about this application in mariculture in general, in aquaculture. So globally, it's the fastest growing part of food industry, with 20% of fish stock in EU coming from aquaculture. Also, in total, on the level of EU, 80,000 employments come from aquaculture, and these are data from a few years ago. So this, for sure, even increased by now. So going more locally, just in Croatia, even 21% of Croatia's fish stock come from aquaculture. So this is a sector with a significant and constant growth. The main research objectives of the Hector project, having more to go from the economical, let's say, objectives and possible improvements to a wider concepts and contributions to the public and society as a whole, was the analysis of procedures in viticulture and aquaculture that are sometimes quite tedious, quite dangerous even, and mostly performed by humans. So we had the goal of determining processes that robots can take over and also improve. And to do that, we had to find innovative solutions how to substitute human labor in harsh environments by using a multi system. So in Hector, as I mentioned, two use cases, one being viticulture, which is not in the scope of this workshop, of course, related to all-terrain mobile robot and a flying drone doing autonomous inspection missions in vineyards. And another use case was the collaboration between an autonomous surface vehicle, a flying drone, and a remotely operated vehicle integrated onto the ASV to perform autonomous inspection missions in around the fish cages, basically. So to do this, we first had to develop our own in-house made autonomous surface vehicle, or catamaran rather, we named Korkira, which is a 2x1 meter aluminum hull catamaran, having an option of payloads of 50 to even 100 kilos with 40 to 100 thrusters in the next configuration to enable it better maneuverability in cluttered environments of around the fish cages, but also booster motor, as we called it, electrical Minkota motor, for example, when the catamaran would do like survey missions or coming from the shore to the fish cage itself. It's a continuity of design from our previously developed ASV named APED in our lab. And as I mentioned, the payloads, they can be quite various set of sensors and subsystems. To name a few, a tether management system for the ROV, a landing platform for the flying drones, surveillance cameras, LiDARs, the acoustic localization system for the ROV, also a multi-beam sonar, so it's quite expandable system. The ROV that we integrated with the autonomous surface vehicle was the Blue Eye Pro ROV from the Norwegian company Blue Eye. I'm sure many of you have heard of. It's a 300-meter depth rated ROV with 2 hours of autonomy, which were quite enough for our application. It has a full HD camera with a tilt angle control, also the lights, and internal IMU temperature and inertial pressure sensor, giving it quite precise depth measurement. So the flying drone was developed in the Larix laboratory from our faculty. It's a medium-scale carbon fiber quadcopter that has an autonomy of around 30 minutes flight time, having in mind that its payloads are the Velodyne LiDAR sensor, so Sony RGBD camera, also multispectral and thermal cameras. So the first step in our project that started in March 2022 was to first procure, for example, the ROV and start developing the ASV, but also making this driver or the interface for the Blue Eye Pro SDK in ROS2. That was the first step of our lab towards doing things in ROS2 to future-proof our software, so to speak. So we can see all the ROS nodes included in this package on the right, and also the graphical user interface that we developed, trying to mimic the graphical user interface in the mobile app of Blue Eye. So landing platform was one of those subsystems enabling cooperation between 2 heterogeneous robots, in this case the autonomous surface vehicle and the flying drone. So the landing platform was developed in various versions, so to speak, and the idea was to enable the drone to stick itself to the landing platform once it lands on the catamaran, and then the hands of the metallic hands of the landing platform would secure it in place. So here we see just a few videos of the landing platform performing. Yes, so these are the trials from Biograd na Moru from 2021 with a static drone. We also have videos which are not shown here, unfortunately, of the drone literally landing on the platform and the platform closing. So another system that we needed was the acoustical system for underwater localization of the ROV and its relative position with respect to the ASV, and not only for enabling precise control of the ROV with respect to the catamaran, also with respect to the fish cage, but also the control of the tether management system, giving the tethered slack to the ROV. So we opted for the water-linked underwater GPS G2 system, since it was, to be honest, the most affordable one, which was proved to be quite precise. So it's basically an SBL system with 4 topside antennas with a baseline of at no less than 2 by 2 meters, at preferably at different depths to enable trilateration of the bottom unit, which is a standalone USB-C charged unit. The operational range that we bought was 100 meters, but Through software, it can be enabled up to 300 meters, and the ping rate was 2 to 4 hertz, which for our application was more than enough. So we made also ROS2 integration, enabling various modes of operation of the UWGPS G2 system, and whether to feed the IMU from the catamaran, which was of better quality, together with the GPS to get georeferenced measurements, or to use onboard IMU and GNSS sensors on board the UWG GPS G2 system. So here we see just a short overview of pool results, which are quite challenging in our relatively small 8 by 4 by 3 meters depth pool in our lab in Zagreb. But we also see that the accuracy is better than half a meter with respect to the ground truth, basically. So for our application, this was also good enough, because also we had a camera on board the ROV that we could use somehow to estimate the distance from the net based on the a priori known size of the openings of the net. Here we see some results, animation from our field trials in Biograd na Moru in Croatia from 2022, following Breaking the Surface workshop that we organize every year. And we see here shown in blue is the catamaran, and in red the ROV being tracked, and some outliers, of course, that were then filtered out. So another subsystem that enabled the cooperation between the ROV and the ESV Korkira was the tether management system. This system was also completely developed in-house as a separate system that could be easily mounted in the front of the catamaran Korkira, and also plugged its power cables and all USB and Ethernet communication in an extension box using waterproof connectors, and the extension box that we also developed for ease of using many payloads that we tested with the catamaran Korkira. So the total length of tether that we bought together with Blue Pro ROV was 400 meters, and it's quite a thin 4 millimeter diameter cable. All in all, given the size of the drum of the TMS, it would be wound at most like 16 layers, and each layer having 59 windings. So for this, we used also slip ring to send the communication from the box of the tether management system to continue the communication through the cable towards the ROV. We use the worm gear transition to use it as a brake, basically mechanical brake, so that the drum wouldn't roll when the motor stops working. And we also tested it in the pool and at sea. On this slide, we see tracking basically of the tether management system control with respect to the distance of the ROV relative to the ASV shown here in green, and then the tether length being unwound with some slack length being shown in red. Of course, there are some outliers to acoustical localization system shown here as spikes in blue color, but they are filtered out, then smoothed out, and also this adaptive change of reference for the TMS system control to reach. And we see that the error of the TMS system is more or less kept constant with respect to the defined slack of the cable. So another interesting and the last part of this presentation is this biofouling estimation framework that was developed. And the idea was to have a solution to estimate directly from a monocular camera video stream the percentage of the fish net being covered by biofouling. Biofouling is, of course, as many of you know, already a big problem in fish cages, constructing the flow of the water and also increasing the dead fish, basically. So the idea is to have a segmenter based on the rectified video, and then to process the contours to detect the net, the size and the distance of the ROV with respect to the net, given the known, a priori known size of the openings of the net. And then to reconstruct this net, to cluster the colors of the algae in this area for a huge data set that we collected to train the logistic regression model, and then to subtract basically the simulated ideal net image from the real image that was taken, and then estimate the percentage of biofouling in the images shown. Of course, the idea would be then using the acoustical localization system to make some sort of a mosaic or adaptive sampling of all these images at a lower frame rate, and then to, in the end, estimate the total biofouling of the net. Of course, we had many sea trials starting from 2021 and ending in 2022. The first one being just for basic controls of the Korkira, second one at Ugljan in Croatia at Fishery Cromaris to collect the data sets. Then BTS 2021 to test Korkira with LiDAR cameras and also the landing platform with TMS, and further TMS experiments in Bistrina close to Dubrovnik in April of 2022. So with this, I conclude my presentation, and the floor is open for questions.
Thank you very much. Nadir Kapetanovic. I don't think we open the floor for questions right now, but I want to welcome the next speaker that is here in the room. It is Associate Professor Irfan Hussain. Irfan, you're here. And you're the Associate Professor at the Khalifa University, right here. Sorry. You're going to present towards autonomous underwater robotic systems, and I think Zenon has your presentation.
You have?
Yep.
Okay.
Yes. So yeah, we're going to hear about towards autonomous underwater robotic systems for aquaculture applications. The floor and the mic is
You can put in slideshow.
yours.
Yeah, just 1 second. It's just opening. So
It will be quick if I will put my.
yeah, but then we can't get on the Teams for the people that are watching online.
Okay.
It's just quite a large presentation, so it just took
Okay.
some minutes. So
I don't think we could
There we
open for questions either way.
do you want to put your presenter mic
Yeah.
on? Yeah.
You don't have the, right? Okay. Yes.
You just turn it on, and it should work. 1 second. Try again.
I can use that.
Yeah, it's you can use the arrows.
Okay, good afternoon. Thank you for the invitation to talk at this workshop. I am Irfan Hussain. I am an assistant professor at Khalifa University. And one of the projects that we are working is aquaculture construction using ROVs. So Khalifa University, as you know, is also the host of IROS, and in 2017, there was a merger between Khalifa University and Master Institute, and as a result, we have a new Khalifa University. We have it's relatively new university, but I think we are making good progress in various areas of research. At the moment, we have two campuses. One is main campus, and the other is SAM campus. We have also organized lab tours for our labs, and you are welcome to visit our labs, particularly in robotics. We have a robotics center, which consists of around 90 plus researchers that are postdocs, graduate students, and faculty members.
working on quite interdisciplinary projects that are related to aerial robotics, marine robotics, manipulations, and also we do have the facilities outdoor for testing our robots, and also the other areas that are related to being. So some of the projects that I am particularly working on is into healthcare robotics, where we are developing the technology that is related to exoskeletons, for example, to provide the assistance and rehabilitation for the stroke patients. And the other devices that I have developed is what is called the extra robotic limbs, supernumerary robotic limbs that are useful for the chronic stroke patients, and both for the fingers and the arms. And some of other works that probably during your technical visits you will see is related to agriculture robotics. So we are in the process of building the autonomous greenhouse that will be consist of multi sensors that includes the thermal cameras, spectral cameras, and the robotic systems to perform the tasks that are related to, let's say, yield estimations, the monitoring of the crops, the disease identifications, and so on. And we do have also some other activities, which probably when you visit, you can visit our booth or you can visit our labs. And one of the projects that we have is related to animal conservation, where we are building a Ubara robot that will be used to interact with the natural Ubara to record their behaviors and also to interact them in a seamless way. So we use our AI model to detect their behaviors and possibly generate those behaviors. So these are the projects that we are working on. Of course, there are much more to say, but I would like to come back to the topic of this workshop, which is around marine robotics, in particular aquaculture. So in marine robotics, we have our marine pool with the waves and streams. So you can generate these waves, you can measure these waves. We will have also the tracking system, above water tracking system, underwater tracking system, also to localize the robots. So this is the great facility that we are using to test some of our equipment. We have multiple platforms that consist of ROVs and USVs, and we have a couple of funded projects that are related to coral reef inspections, aquaculture inspection, and also the plastic ocean, plastic cleaning. So these are some of the activities that we are doing in our underwater pool. So we also started collaboration with the Stanford University, where Professor Osama has developed Ocean 1K, and particularly he's using the haptic interface to teleoperate this robot, and then also have the sense of touch as a feedback. Particularly, the robot can go to 1,000-meter deep, and you have the tactile sensing to these haptic interfaces. And I think tomorrow he has also a talk, so he will be talking about some of the aspects of this. We also participated in NAMBIZ IRC competition. We had a joint lab with the Beijing Institute of Technology, where we got the third position in this competition. And again, I think this morning, in the talk, I explained about the different parts of that competition, which was related to localization, navigation, detection, and manipulation. So I would be going fast. So these were some of the assessment stages that we passed to go from the semi-final to final stage, and these were some of the tests that we did during the actual performance of the competition. Of course, the competition was the GPS denied environments without using the GPS heterogeneous systems, where they need to together need to perform the detection task, that is detecting the target and also look like then picking the objects and bringing to our USV. So we also established a joint lab with the BIT, where we are focusing on one of the projects that is related to port security inspection. And another project that we have is related to coral reef inspection. as you see that for the coral, at the moment the human divers go inside the water. Of course, it's extreme environment. It's not safe. You need a very expert diver to do this inspection, and the divers go with the coral watch, and then they used to put the coral watch next to the coral and then try to label the colors changes and also try to classify the corals. So what we want to do is we want to use the ROV that will be mounted the coral watch, and then we want to repeat what the human divers used to do using our AI algorithms. Another problem with the coral particularly is the starfish. So again, the human divers used to detect that starfish and used to inject the salt that helps to remove, to control the population of these starfishes. We have developed a solution to autonomously detect these starfishes, and then we have a tool that helps to perform the intervention task that the human is doing. So these are kind of the experiments that we have done in our pool, where we simulate the whole exercise of autonomously detecting the starfish and then having this tool to inject the salt inside. So these are some related projects. Lastly, I will come back to aquaculture, what we are doing. Obviously, it's very hard to speak after the talk of Alini and what great work you guys are doing. We are relatively new this two area, but we are focusing on more about the computer vision algorithms and also the autonomy and some algorithms that we have developed. So obviously, we all know that aquaculture is facing challenge that are related to net biofouling, vegetations, and net holes, and many more basically. And there is a very clear need to advance the AI-based inspections and monitoring methods. While we see that these current traditional approaches, which are the human divers based, face many challenges. So there is a clear need to come up with solutions. At the same time, when we started this work, first thing that we realized that there was not many data sets that are associated for the aquaculture. And if you want to work with AI models, first thing that you need is the data sets. So we started our work in this aquaculture net inspection. We basically tried to develop a data set that maybe can be used for the community, people like us. Of course, it's a very basic data set that we have captured. And this first paper that we had published. Then we are also working on the novel deep learning transformer-based models that help to do the inspection using these data set. And lastly, we are interested to real-time aquanet inspection using ROV. And at the same time, we are also handling some of the challenges that are related to image enhancement for the underwater. So we have proposed algorithms related to novel underwater image enhancement. And finally, we recently also started the integration of the vision-based AI models with the large language model. So these are some of the contributions that we recently had made. So we started dataset collection in different locations, both from the BUST and also the KU at the KU setup. And we extracted the images and annotated them after the detection. We performed the data analysis that tell us the number of images, classes, and distributions. And then we trained our algorithms to test the existing vision models, and similarly we propose our own models that using this data set. So the kind of the data set that we have, it has the information related to biofouling, vegetations, and holes. And we have the BUS data set. We have also data set that we have created in KU. And then we basically trying to open source this data set as well. And then basically we use the blue IROV and the five-fish to collect the data sets. And in particular in the KU, basically we create this kind of setup which resembles the net holes, for example, the vegetations and something related to biofouling. So the samples of this proposed AquaNet dataset consist of this biofouling, vegetations, and net holes. And this data consists of classes in various sizes, shapes, and also the visibility. And here you basically can see the different existing vision models that were applied on this data set. And we first train the models and then we test on the proposed data set. And these models definitely struggle in detecting the net particulate holes, and also they showed very poor performance on the biofouling. So this gave us the idea to propose a novel multi-scale encoder decoder topology that can be used to enhance the accuracy of the detection. So it basically the proposed model consists of an identity block, then it has hierarchical block, and also the shape observation block. So we then again tested our proposed model on this data set, and here you can see the qualitative evaluation of the proposed model on the KU data set, and where you can see that the first, third, and fifth column shows the original images, and then you can see basically the results of our algorithms in detecting the holes, the biofouling and classification. While on the right side, you can see the biofouling detection on the lowest data set. So clearly we saw that our proposed algorithms showed a better performance as compared to the traditional approaches. While in our marine pool, we just set the experimental setup because later on we wanted to apply these models on the ROV and wanted to perform the experiment in detecting these holes in real time. And for this, we set up the experimental setup, which has a garden pool and has a large net and ROV. And we applied the proposed approach using an online framework for the net inspection, which includes the vegetation, holes, and plastic detection. And the proposed deep learning model is coupled with the ROV method that focus on detecting the irregularities into the aquaculture environment. And we basically, as you see that these results obtained during the aquaculture net inspection, the algorithms in real time was able to detect these holes, vegetations, and with the help of our ROV. Then we performed the comparative performance of the state-of-the-art algorithms that consist of yellow 4, 5, 6, 7. And we evaluated their performance, and then as a result, we saw that yellow 5 performed better as compared to the other these models. Then, but one of the great problems that we saw is that in the underwater images is the quality of these images. So we have further proposed the algorithms to enhance for the enhancement of the images of the underwater, and and in particularly we proposed algorithms that's called Bulldog, which basically it improves the performance of the traditional TAN method. And this is the work that we have recently published in another top 10% journal, where we perform the extensive evaluation on our very diverse data sets that have the very different types of the underwater images. And then we compared our model as compared to the state-of-the-art model. So lastly, it's great that recently the vision-based models are showing their potential, but as you see that vision-based models, although they are very good in detection and segmentation tasks, but they do not provide any contextual information about the theme. So for this, we thought to integrate the vision-based model with the large language model, do not provide the information only the image, but also you have the contextual information. So this is recently work that we have done. So as a result, we have these qualitative results which showcase the detection using the computer vision algorithms plus large language models. And it describes the result in a contextual format and also as well as it segment the images. So in a summary, basically our contribution related to aquaculture is one is proposing a novel data set that can be used to benchmark the computer vision algorithms, and also proposing novel detection models and image enhancement models, and also integrating the vision with large language models. So this is the current status of our work, and thank you very much. Lastly, I just want to introduce that we also started a robotics program recently, offering a bachelor and master's degree in robotics. Thank you very much.
Thank you very much, Khalifa. Thank you. Thank you for the overview of what we do, and I'm especially impressed by the pillar ROV. Maybe you heard more about the methods, but I thought about the starfish. The next presenter I've been looking forward to introduce is Professor Maria Rusma from Tallinn University in Estonia. She's going to present to us the bio-inspired robotic system UCAT for operations in Atlantic fish farms. Thank you for being here, and here you are.
Thank you, Christina.
Do you want to try this thing, or do you want to just use the arrows to go back and forth?
Arrows look like more reliable. Yes, yes.
If it's analog.
Yes, keep it analog. Thank you very much for still stayed here for the afternoon. We heard a lot on before the break and during the sessions that it's important to have a moving monitoring devices in sea cages because it will reduce the cost. And it's also very important in fish farms to guarantee the welfare of the fish. And it's for the reason not just to make the fish happy, but also because happy fish will produce more yield for the farmers. So it's kind of win-win solution for the farmer and for the fish to keep them healthy and happy and less stressed. And then we come to the problem that if we want to use robots, what kind of robots should be them and how should they behave, or how kind of robots should be used to maintain the fish farms so that we don't cause any additional stress for the fish. And it's also important to understand that when we go in close to fish, we're disturbing them. So if we want to know if the fish is acting naturally, we need to have something which is as little as invasive as possible to understand their natural behavior. And actually, this problem is very widely addressed by biologists before. So they using the sort of animal playbacks or devices to observe robots, animals in natural environments all the time. You could see from the previous talk with a bird, actually they are falcons outside, if you notice them when you came there. I first was convinced they are robots, by the way, and it took me a long time to understand they are not, they're actually actual birds. So it's not so hard to say that the bird will think otherwise, right? It says like it's an actual bird, but actually it was a robot. So it's known from biology that sometimes and often animals react to very special cues of the robot, which is called the trigger features or trigger events, in order to exhibit a certain kind of behavior. And in our case, if we want to observe the robots, that would be the avoidance behavior. We're going to have a robot that does not trigger the avoidance behavior of the fish. And seems to be stuck now. Okay. And also we have quite a large body of literature already, or significant body of literature investigating the behavior or interaction with fish and fish robots. Honestly, it seems like to be a peculiar thing to do, but actually many researchers do that. They have in the labs, they have model fish and they have model robots, and then they try to find out what are the key triggers or the behaviors of the robot fish that triggers some kind of the behavior of the real fish. And these are offering very interesting insight to what fish actually behaves like. But the problem with this is that it's very hard to go from the lab experiments and have a very general conclusion about what we should do in the fish farm. we have to be very careful with this sort of a generalizability from one fish species, for example, to another fish species. You wouldn't do that for a mammal, right? If you go into the lab and you do experiment with the mice, then you wouldn't say, oh, my mice was reacting this way, therefore I think a polar bear will react to the same way. Or I didn't know, a flock of migrating lemmings in Norway would do the same thing as a mice rat. They won't. And the same thing holds definitely for fish. So they're very, very different from each other. And there are like 34,000 fish species, where there are only 7,000 mammal species. So the variability is probably much bigger there. And in a lab condition, we normally use some model species. We do them for a reason. They're easy to keep, and we can generalize from that. But it's very hard to say that, you know, when you have 200,000 individuals in the salmon farms that would do the same thing. And of course, when you come from a lab environment into the natural environment, there is actually an environment in the middle, which is normally called a mesoscale. It means that it's not like observe in a wild, but it's still kind of constrained, and you can control some parameters, but you can't do all of them. So it's kind of a transition phase between a lab and between the real life. And a fishing net is a very good example of this sort of a mesoscale environment. Some years ago, we made a testing with mackerel in fish bin with 3,000 individuals. And likewise, in a lab experiments, we had a liver robot, halfly actuated robot. And since we were looking at the lab experiment, we thought it's really important that the robot will wiggle its tail and it moves, is at the same size and so on. So we tried to have robots going through the mackerel and moving the tail and going at different speeds. And what we actually understood in the end, that some of the cues which are really significant in the lab environment are not significant in when you scale it up. And we don't know exactly the reason why. For example, it didn't have any tendency to react to the tail motion or, the hydrodynamic signals from a tail. And I think it's just because the same reason here. It's very much noise here, so you hardly have hard time to hear me speaking, right? So now think it's one of those mackerels out of 3,000, and then you have to pick up the cues for somebody that is going through the net. So what are you relying on? It's only things that you can rely is something very, very rudimentary, very, very primitive things. And it's probably the speed and the size that comes out from my research. And it kind of makes sense because mackerel, it's a predator, it's a pelagic fish. It's normally not kept in fish bins, but this one was because of the experimentation. But the only natural enemies that those fish are actually orca whales. And when they're gliding in, okay, what are you afraid of? Speed and size, right? So you better take off before something happens. And this is kind of makes sense that a fish react in this way. But one of the more general conclusions that we made from this research was that if you want to observe the robots, you don't have to have a very complicated robot. Actually, those cues could be pretty primitive that trigger the avoidance behavior. And if those cues are not there, you're pretty safe. And we know that cost is important. You don't want to make your robot too complicated if you want to scale it up, if you want to really, produce and sell it to the farmers. So it's really important to know that what is really those things you have to take into account when you're producing your technology and what you don't really have to care about. And from there we got also an idea to use one of our robots that was developed for a completely different reason. We first developed it for underwater archaeology. And it's a fin-propelled robots for a reason, because we wanted to have something that is very quiet and very maneuverable. This one was specifically, as you can see it, develop our shipwreck penetration. So we wanted to have something that is small, goes into a confined place, turns around easily, and doesn't disturb the water because it's beats up the symptoms and you can see anything. But we thought that once we have this robot already, it could have those features that are already interesting for observing fishes and fish farms because it's small, it moves quietly, it's maneuverable, all those things that you need in a fish farm. So we went on and we wanted to see if it's really an advantage to have this sort of a bio-inspired robot in a fish farm. And we made a very as well controlled experiment as you can see in a mesoscale environment to compare it to two different intervention technology. One of them is a human diver, which you heard already. It's still a most used technology in a fish farm for inspection and maintenance. And another is ROV, which is also quite often used in the maintenance for the maintenance in fish farms. And in addition with that, we also refined the experiments with the bio-inspired robots. So we had different parameters that we controlled. We wanted to know whether there is a reaction to a color. We wanted to know whether there is a reaction to actuation mode, and when it's completely quiet. And from there on, we designed the experiments as well as you can do in the mesoscale. So having a camera looking upward and then having the device for a diver, which is also equipped with a GoPro, taking videos, and then in these situations, comparing them to each other. So from this video, you could see that the little robot has actually two different modes. One is a hovering mode, so it can be very fine-grained motion, for example, station keeping. And the other mode of locomotion is a cruising mode, which goes a little bit faster. And you could also see the relative size of the two robots with each other. And this is, you can see the picture from a camera looking up from the bottom. Here you look the diver, and you see no fish around it because also fish have taken off. They didn't like the driver. And you could see Argus Mini, and here you can see also the UCAT robot. From there, you could also already say the fish come closer to the UCAT robot, but we also wanted to quantify it. So from these pictures, we also measured how far the fish get, and from a GoPro, we were also measuring the tailbeat frequency of the fish because we took it as a proxy of how disturbed fish are if they are in a natural environment where Oh yeah, that was actually from my video. I'm coming back to that sound. And making a comparison between those technologies. Then, main finding was actually something that was quite well consistent with our previous experiment is mackerels farm, saying that the size really matters. If you're really, really big, then it's probably the fish is going to be afraid of you. And for some reason, the fish were much more showing the flee behavior for a human diver. So it's like we're getting far, far away from the human diver, but we couldn't figure out for what reason. Was it the size? Was it the shape of the diver? Or was it the color of the diver? Or was it the rebreather? Or bubbles or something else, but they were really, really going away from the diver. And it's definitely said that if you want to observe robots if you want to observe fish in their natural environment, you shouldn't dive into the net and go see if you can see all the, subdominant fish somewhere who are, undernourished or something. They probably gone away long before you go into the net. It's a little bit better with the mini Argus. And with a small robot, it's really best. So they're quite relaxed around that. And the other thing is, again, consistent with the mackerel experiments, as I said, speed is really what matters. Even if you're big, but you're moving slowly, they're happier than, when you're small and moving fast. They don't like that. And of course, they don't like if you're big and moving fast. So that's something that they're really scared about. as opposed to what we expected to see, there wasn't any significant difference in ways the small robot was moving. So we kind of also expected to have, like, I don't know, hydrodynamics to play a bigger role, but there wasn't actually anything like that. And how we move the pins or how fast we move the pins and so on. And also, we didn't expect that the fish were so indifferent about the color of the robot, because we thought that, if we make it of the color of the predator, for example, it would look differently, but it didn't. So it didn't really matter. And last but not least, what we were really surprised about, you heard the noise. And we thought that fish don't like that at all. But there wasn't absolutely difference between whether the robot was moving and making the noise, or if the motors were switched off and it was not making any noise. So we don't know exactly why. Could be different reasons. Could be that they just have been adjusted, or they have the noise around in a fish farm all the time. We have no idea. Or actually, you here have idea how noisy the fish farms are actually, so they're probably used to the noise. Another thing is that this noise the robot is making is outside of the bandwidth of the hearing, perhaps. So that could be another reason. The hearing limit of Atlantic salmon is about 800 kilohertz, 1000 kilohertz, or something like that. So it's outside of that, it doesn't really make a difference. Right. But a more general conclusion from that one is that if somebody would ask me what kind of robot should you make, instead of making a very complicated one, which is, I don't know, salmon shaped and speaks like a salmon and tells a stories like a salmon and looks like a salmon, I would say it just has to be small and it can't be moved too fast. It's as simple as that. And it's a very kind of disappointing result for a researcher, because you definitely would like to find out something very interesting, like, I don't know, a robot that winks your eye and, shakes your head is approved by fish and the others are not, but it actually isn't. But I think it's a very good news for anybody who is developing technologies for the fish farms, because most of the things you don't really have to take care of, and you don't have to make them complicated. All the bio-inspired robots tend to be complicated. They have very many moving parts, which means they're very complex, and this makes them expensive and also less fault tolerant. And in order to just, let it go would help you to save costs. And in the end of the day, I like you to think about that a fish actually has no concept of a bio-inspired robot. So the fish doesn't know whether your robot is supposed to be bio-inspired or not. So you haven't cared too much about that. And maybe final conclusion for that is that I already in the beginning said that we have to be very careful from generalizing from a lab to mesoscale to natural environments. And I'm still saying that, because even with our experiments in a fish farm, I could see that, in one net, for example, say fish got scared much more easily than in another one. And maybe from year to year, maybe from species to species, it varies. So definitely, if we are criticizing lab experiments for the same reason, we should also be careful with over-generalizing on the little research we have on fish farms. But I thank you for that, and I'm looking very much for next presenter.
Thank you so much, Maria. It was very interesting, although the boring result was interesting. Now we have the last quarter, 15 minutes gift of today, and it's going to be on block. No.
Two more.
I'm very sorry. I almost, and I even have your name here. Mohit Singh. You are saving your professor, I think, by coming here today. Mohit Singh from Department of Engineering Cybernetics at the Norwegian University of Science and Technology. You are going to present resilient, exclusively vision-driven underwater autonomy. Thank you very much.
Thank you so much. Yes, so hello everyone. I'm Mohit Singh here, and I'm presenting on behalf of Dr. Kostas Alexis, who is my advisor. So a little bit about me. I'm a PhD student, and it is actually interesting that I started my journey in robotics long back, but EdNEC has a contribution to it, which is it was my first international robotic presentation back in 2013. And so far so good because I'm still in robotics. So, but yeah, let's go. So we are talking about mostly vision-based or vision-driven robotics, underwater robotics particularly. And the question one is why vision? A brief answer to that would be first the advantages of vision, which particularly are the passive nature of the sensing. So we do not emit anything. It's very ubiquitous sensing as well. It can be found in many shapes and many forms actually. There is a huge selection of how you can select a camera depending on the needs. And it provides rich information, of course, when it does only. Like if you see something, that does provide rich information. Now, the challenges of underwater robotics, of course, with vision are your physical conditions themselves are varying. So, for example, your refractive index might vary, your temperature varies, and so on. There's low illumination, there's visibility challenges, and there are noise and moving bodies like fish. So in this line of work, I would first try to bring the attention toward moving or varying quantities, for example, refractive index in water. And what we do for that work is particularly we estimate the refractive index itself. And that is being presented here in online refractive camera models. Now, of course, the motivation here is that when people do calibration underwater, they try to use tools which are attuned to lens distortion. However, this does not account for the refractive distortion of water. And also, if you just calibrate your camera in one particular setting, the refractive index itself can change due to many properties of water. And also, calibration in water is also very laborious. So you have to move your robot around, or you have to take your camera and move around your hand. What we propose here is basically a camera model which integrates the refractive index in the model itself. And going forward, at the root of this concept is basically that when you have refraction and distortion due to refraction, what you essentially have is these warping which are in the form of a hyperbola. And this hyperbola is parameterized by refractive index. Now, if you can make this hyperbolic line a straight line, then you have corrected for refractive index. And that's how we estimate the refractive index itself. A little bit of maths here, but the whole idea is that we can choose the features between the stereo images. And given those features, we can estimate the refractive index for each of these features. We do some filtering, and we take the mean over the image, over each of the pixels which we match. And this allows to estimate the refractive index and use the refractive camera model to calibrate the image and remove the distortion. Now, for experiments, what we do is we have an underwater robot. It is mainly, again, a vision-based robot with 5 cameras on the top. So you see 2 cameras, a stereo pair, which is the 2 cameras in front, camera 1, camera 2. And then there are side cameras, and then there's one top camera. Of course, the robot also has an IMU. Now, going forward, this is the first result which we have, which is basically we have feature matching going on the top and the method estimating the refractive index in real time. So if you see, the method starts from somewhere 0, and then it goes to 1.33, which is the ideal refractive index of water. And thus it calibrates online for the refractive index. And we also see some enhancement in the odometry result due to estimating the refractive index and not relying on calibration, which has been done in water. Now, one more thing this allows us, which probably can also be seen in biology, which is this allows us to adapt in real time while we vary the media, which is we go from water to air, and the method estimates the refractive index. So for air, the refractive index is 1. For water, it is 1.33. And this can be estimated in real time and be corrected in real time. So this can also allow methods which can work across media in real time. Now, okay, we can estimate the refractive index. The second question would be, and this is a work which I'll be presenting in much more detail on Friday, but the second question would be, can we integrate this refractive index and do all the distortion and all in a much more integrated manner? Because the past work was, it was using stereo cameras and it was a separate module. All the work of visual inertial estimation was happening later on. What we do in this particular work is we formulate the refractive index as a state of the Kalman filter and estimate the refractive index in the Kalman filter itself. Now, again, what we do particularly is we take the refractive index, refractive camera model, which we described earlier. We take that, we cascade it with the lens distortion. So for that, we use the equidistant distortion model. And the equidistant model is calibrated in air only. And that's what the main essence of the work is, that you only have to calibrate your cameras in air, and it will generalize to water. But and particularly now what we do is we have a monocular camera and an IMU only. So no stereo, just a monocular camera. So we have the robot state, which is the position, velocity, angular velocity, at orientation, etc. Then we have the refractive index in the state of the Kalman filter. And then we have state related to the features which we are tracking. Now, we of course need to derive some quantities for the refractive index and how these quantities are changed in the framework of the visual inertial odometry, but not going too much in the maths. But main idea is that we rederive the innovation term of the filter and rederive the Jacobians, and that allows to estimate the refractive index. And this is one of the results which we have. So for example, we initialize the refractive index at 1.33 or 1.35 actually, and then it converges in real time to 1.33. The bottom plots also show the trajectory which we estimate. And basically the colored plot is showing the error from the ideal value. So more yellow it is, more lower the error from the ideal value of the refractive index. And you can see it actually converges in one lap, and in last 2 laps, it is converging and is very close to 1.33, which is the ideal value of refractive index for water. Going forward, other question would be, is the method robust? So for example, if you initialize the refractive index with a very wrong value, which is what we are doing here, we are initializing the refractive index at 1.6 and 1, which are very far away values. But in both cases, the refractive index converges. And basically, what this allows us is to not calibrate the camera in water for underwater robots, just calibrate the camera in air and just let the method estimate the refractive index and let the robots run in water. So there are some more diverse results, and some in low light condition, some in good visibility condition. Now, one thing to notice is in the low light condition, the point cloud is also much sparse because you cannot match that many features. But okay, so now we can do some vision underwater. And what we are doing now is we are using a learning-based method to do stereo depth estimation. And that allows some mapping capabilities. And particularly what we are doing is we are using raft stereo, which is a learning-based stereo method. We are using that. And then we are filtering the point cloud with the depth confidence. And that allows us to do reliable mapping underwater. And then this mapping is also using the odometry result from the methods which we used earlier. Now, okay, so what we have now is we have odometry, we have mapping framework. What can we do with this now? And before we go to that, which is, of course, if you have odometry and mapping, you can enable some form of autonomy. But one question for underwater particularly is you may not have vision everywhere. For example, your robot may just be looking at the fish, for example, in aquaculture or even in general, it may be very possible that you're not looking at something meaningful. For that, what we develop is deep PL, which basically bridges the perceptual degradation regions. And what it allows is you to do state estimation with complete blackout. So for example, the method in the green trajectory is getting with zero images, but what it is getting is from deep PL, it is getting the velocity, and that is integrated in the extended Kalman filter, and that allows it to do velocity aided estimation. Now this, what we demonstrate with this is in control settings, it allows you to do almost as good as performance as BIO. But now we have to test it in more difficult situations for sure, right? And what we do here is we test the method in Trondheim Fjord on a trajectory which is 230 meters deep, 230 meters long, and with approximately a duration of 440 seconds. And here what we see is roughly the error which we get is about 3% relative error for the positioning. But again, this method is only getting velocity from the DPL. It is also getting barometric adjustments for Z, but in X, Y, it does not have any other constraint than the velocity provided by the network and complete visual blackout. We also test this method on diverse set of trajectories. So we take 6 of these trajectories are collected in the fjord, and maximum length of the trajectory is, I think, about 300 meters. I'll quickly skip to one more slide. Yes. Now, what another question would be, can DPL allow something like position status, position control when you have complete visual blackout, which is actually a very important question, because this then brings us to, can we do functional autonomy in when we have complete visual blackout? And that's what we tested in this result particularly, which allows us to do position control in complete visual blackout. And what the robot trying to do here is basically go around a square trajectory. Okay, so now we have some odometry, we have some mapping, and we can bridge through the regions of visual degradation. Now, if you know about Autonomous Robots Lab, one thing which the lab has in its direction, which is very clear, is most of the work comes from aerial robots. And for aerial robots, there are many methods which have been developed in the lab. And one question would be, so if perception is somehow solved, or if we have reliable perception, can we use the methods used for aerial robots for underwater robots? And that's where some of the next results come. Now, what we are showing here is this is an aerial robot, which has a learning-based method. It takes depth image from the depth camera as the input. It takes partial state, and what it is trying to do is avoid the obstacles around it and go to the goal. So this is for an aerial robot. Now, can we do the same for an underwater robot? We can, given reliable state estimation. So of course, this is a simplistic environment, but it still allows us to do state estimation. Then we do depth estimation, and given the depth estimation and the state estimation, we can use previous Oracle, the learning-based planner, and that allows us to do learning-based path planning underwater. So as you can see, these pillars or these columns are the obstacles. Another method which has been developed in the lab and which has received quite some attention in the past few years is graph-based exploration path planner, or GV planner in short. And it has been quite essential part of the lab solution in DARPA Sabti challenge, which also made the lab win. So basically, this path planner is for exploration path planning to explore the environment. And we deploy something like that on an underwater robot as well. And what you see here is this ROV taking all its 4 cameras on the 2 in the front and 2 in the side, doing the state estimation, making the point cloud, and exploring the environment completely autonomously. So you can see the paths generated by the planner, which allow it to completely autonomously explore the pool. Now, since the workshop is about aquaculture, I'll quickly go over results from something which we did very recently in a fish farm. And mostly the main mission here was to collect data, and then we ran some of the our methods on the data. And what we have here is the robot in the fish farm, and we are able to run the state estimation on the fishnet. Now, one challenge with fishnet, even if it is visible, is that it is a very self-similar environment. But that is mitigated by the visual inertial estimation method, which we are using, which is based on Robio. So it does IMU-based prediction, and that allows it to not be reliant on the distinctness of the features. But anyhow, we are able to map the environment, so you can see the curve of the fish farm. And of course, there's a lot of fish in the fish farm, which can be a problem to the robot, but mostly it is very robust and is able to navigate even if some of the fish comes in front of the robot. Now, our goal in very near future would be to enable autonomy in such conditions and to go more about for the low light conditions as well, and preferably in environments which has sparse visual clues. So, for example, the robot can handle some visual degradation from time to time. And that being said, that's the end of the presentation. Thank you so much.
Thank you very much. And I'm sorry that you got quite much competition on the sound, although it's nice. So we're just going on. I've got to say, Mohit, that I think you're onto something with your methods. Now we're going to the last presenter of the regular quarter presentations. It is online. It's from the same university and department that we just heard from. It is the Associate Professor Annette Stahl.
Hello everyone. Thank you for joining me today. I'm Professor Annette Stahl from the Department of Engineering Cybernetics at the Norwegian University of Science and Technology. And today I would like to talk about the potential of robotic vision for autonomous operations in aquaculture. Norway's economy benefits significantly from aquaculture, particularly salmon farming. A typical farming site in Norway contains 6 to 10 circular sea cages, with up to 200,000 individuals in one cage. One cage has a diameter of up to 50 meters and a depth of 20 to 50 meters. And with these settings, aquaculture in Norway, however, faces challenges such as ensuring fish welfare and maintaining equipment integrity while also addressing environmental impacts. Our goal is to tackle these challenges through innovative technologies. Our approach employs vision-based technologies for monitoring critical indicators such as scale loss of fish, wounds, melanin spot fading, and respiration measurements. Vision technology can also be enabled to detect irregularities and potential breaches in fishnet structures, which are critical for maintaining the integrity of aquaculture operations. However, implementing vision technology underwater comes with unique challenges. On these slides are shown a lot of video recordings. And all these video recordings are recorded by one and the same camera during one day. The clarity of these images is very often compromised by turbidity, fluctuating lighting conditions, and other dynamic underwater elements. And these factors make consistent monitoring very difficult. But with modern vision technologies, we are quite capable to detect and analyze parts of salmon, from the head to the fins, enabling detailed health monitoring. This first level of detections is key for assessing the condition of each fish and responding proactively to potential health issues. Building on this, our object detection and tracking systems are designed to identify specific fish parts. Is the head, the eye, and snout of one salmon detected, the head is further tracked. Detections for further analysis include also snout, dorsal and caudal fin, as well as wounds. With the detection and tracking in place, we are able to analyze the mouth opening frequency using an optical flow approach. The detected mouth opening is here colored in yellow, and the closing is colored in red. In the top bar, you can see the ground truth information, and the lower bar shows the actual measurements. One can say that in average, a salmon is seen in a stationary camera 1 to 4 seconds. The mouth opening was monitored under different conditions regarding to temperature and oxygen. We defined the ventilation frequency as the median duration between consecutive motion shifts and received with the introduced method a quite good analysis result, which helps us to understand the breathing patterns and the stress levels of the salmon and provides us with insights into the overall well-being under various environmental conditions. Another important welfare indicator is scale loss in fish. Utilizing high-resolution images and machine learning algorithms, we categorized fish into classes with single scale, small area, and large area scale loss. For the analysis, we utilized a dataset of around 300 images, which were recorded under controlled environments in a lab. The dataset contained varying fish sizes and degree of scale loss. YOLO V8 was utilized to detect the fish and segments it into scale loss regions. It derives, in addition, also a skin mask. Both the scale loss detections are weighted against the skin mask regions in order to derive a quantification measurement. With this particular method, we've received a precision score of 89.4% and a recall score of 79.8%. But does this proposed method also work for underwater images, which state a huge difference in appearance to the training data set? Here you see a first proof concept study and the results received by using very few images. And we received with that a precision score of 64.4% and a recall of 58.8%, which is a quite good result for this very, very small data set we used for the training. Another aspect of our research focuses on melanin spot pattern. By tracking these patterns, we can detect and quantify stress and diseases indicators, advancing our capability to monitor health without direct contact. The melanin spot coverage of the entire fish body is detected, and spot changes in the head regions of the salmon is also tracked over time. The potential fading of the melanin spot might indicate severe levels of stress. And with machine learning technologies, these changes could be monitored over time, similar to the previous method we presented. The melanin spot pattern allows also for advancing towards individual fish re-identification to create unique fish profiles based on spot patterns. This technique is vital for tracking the long-term health and growth of individual salmon within larger populations. This leads us to the very difficult task of long-term fish re-identification. The vast number of fish and the subsea conditions pose a significant identification challenge. By facilitating a biometric fingerprint for each salmon, enabling individual tracking and re-identification over time, we're getting closer to the direction for a personalized health management. The question here is then, can we re-identify an individual under so many individuals? To get an impression, here you see the salmon with a time difference of 10 days. So the same salmon is recorded and you can maybe observe the same pattern at the head region here shown in the video. With this technology, we developed an automated breathing rate respiration estimation system called SAPRE system. This system allows us to observe and react to subtle changes in individual behavior that indicate health issues or stress. We observe during 24 hours different breathing behaviors. During the different oxygen levels, there were the same slow and fast breathers, indicating different personalities. We were able to reliably identify salmon in a population of 63 fish. The mouth opening frequency were monitored, and lower oxygen levels in the tank did lead to an increased breathing rate. These 4 peaks you can observe in the graphs indicate short periods where the cameras were taken out of the tank to charge battery, and this leads to a period of disturbance in the tank, and that caused higher breathing rates of the fish. As a surprise, we observed individual breathing patterns. Fast and slow breathers were observed in the population. But vision technology can also be utilized to monitor the physical integrity or net structure of aquaculture plants as a warning system for maintenance and fish escape. We've developed an autonomous net monitoring system that detects holes and irregularities using advanced computer vision techniques. The net were classified into appearance-based regions, here into black net regions, bright and no net regions. By applying deep learning, a binarized mask was generated so that we could identify no net and net regions. We applied this to real imagery and received a precision score for the net class of 91%. In addition to that, we utilized traditional Fourier analysis to develop a robust pose estimation and distance measurement approach for aquaculture operations to ensure operational efficiency and safety. With that, I would like to conclude my talk and would like to thank our collaborators at SINTEF, NTNU and NMBU. The presented research was mostly connected to the CAGE project, which is funded by the Research Council of Norway. And I would like to mention that the CAGE project was recently selected to be a part of a larger initiative endorsed by the United Nations Decade of Ocean Science for Sustainable Development. With that, I would like to thank you for your attention and wish you a nice day.
Originally, it was a 10 minutes break on the program, but originally we were scheduled, or we are after the schedule now. So we are just jumping right to the 3-minute presentation. And the first one is ready, I can see. Are the other ones that are supposed to be here? They are here and ready. Okay, very good. So can everyone just stand up a bit while standing is getting ready? Can you stand up? Are you able to do it? Yes. So now we don't have music, of course. During the break, we don't have music. But we can just stretch a bit and I'm not taking gymnastics now. I'm not taking dancing either, but okay, so just move. Then you can sit down if you like, or you can just continue dancing while we will have this 3 talk.
Ready?
Yes. Now we are starting with the first of 6 3-minute presentations. Sveino Johan Orem at SINTEF will have his presentation about underwater robot guidance, navigation, and control in fish net.
Thank you, Christina. And also, I see there's a lot of people out there waiting for the reception to start. So come inside and learn a little bit about aquaculture robotics while you're waiting. So my poster, it's mostly kind of giving an overall view about some of the challenges and some of the technologies that exist for navigation, guidance, and control in fish net pen and robots used there. So commonly for navigation, the DVL, the Doppler velocity loggers, which gives you the velocity of the vehicle, underwater or ultra short baseline systems, USBLs, and camera-based navigation, like we have just seen, they are often used. There are pros and cons to many of these methods. The DVL and the USBL, they don't really care if the fish is, no, they don't care about the visibility, but they are blocked by the fish. The visual methods, they need to have the visibility to be able to detect nets, for instance. But most importantly, when we're talking about navigation inside a flexible structure, is that we have to use a local relative positioning. Because the net will move, and it doesn't matter if your robot is located in a fixed position if the net is moving. So moving on to guidance. At SINTEF, we have been working for many years with autonomous methods for one thing that we call net following. And we are currently trying to employ that in an industrial setting, bringing this technology to the industry, which allows them to do autonomous traversals of the net structures with little to no intervention from the ROV operators. This means that the operators can then focus on different tasks, for instance, inspecting the camera images, or maybe even supervising several robots that are doing the same task. We also need to have motion planners for obstacle avoidance, and we have been demonstrating some of these already inside fish nets. When it comes to control, we normally need to control the surge speed, the sway speed, and the heave speed, and the heading of the ROV. We need to have robust control because we have to do accurate operations. You can potentially cause more damage than you're trying to solve by getting tangled into the nets or into ropes, potentially making a hole in the net, which will be a catastrophic event. During a lot of our trials, we have found that nonlinear and adaptive controllers show better results than conventional PID control. As for some future work, when it comes to the navigation part, cost is the essential keyword. The aforementioned technologies, they all cost more than the robots themselves. So it's not necessarily available to many of the companies that are offering these services. So camera-based navigation is, of course, something that immediately is an opportunity. but there still is a way to go to make these systems available to the industry. For the guidance part and the control part, there is a need to do long-term, larger scale trials to prove that these methods are actually as robust as they claim to be. Because currently there's been done short tests only. And lastly, doing more vehicle manipulator control, which could enable the ROVs to do more than just inspect, to actually repair and maintain the equipment, is also something to work towards in the future. Thank you for your attention. And if anyone wants to talk more, I'll be over by the posters in a couple of minutes.
Thank you, Svein. Now we'll have an online presentation before two presentations that with people that are here, and one online and one with a person here. And after that, there will be so many things happening with perhaps the debate and at least award. So now I can present framework for robust localization of UUVs and mapping of netpens by David Bottom.
Welcome to the presentation of our framework for robust localization of UUVs and mapping of netpens. Since the fish farming industry is rapidly expanding and involves a lot of manual and high-risk operations, the introduction of robotic and especially autonomous systems can greatly enhance the sustainability of this industry, thus requiring robust and precise localization methods. This is why we investigated multiple vision-based methods and developed this framework to obtain relative poses, depth images, as well as global poses and three-dimensional maps. Our starting point was a dataset obtained from the SyncDev ACE facilities in Norway. In the first step, multiple point distances to net are estimated using the fast Fourier transform method. Subsequently, these points are utilized in the true depth network together with the monocular images to generate dense depth information. From this dense depth information or the FFT points directly, utilizing shape fitting, we were able to obtain relative poses. Together with the DVL velocity measurements, the FFT points were also utilized to estimate global poses. And from these global pose estimates, together with the depth images obtained from the true depth network, we were able to utilize WaveMap to generate three-dimensional maps. To the net relative results, on the left we see a distance comparisons plot, and on the right the angular measurements comparisons, and especially in the distance comparisons between the onboard sensors, aka the ping and the DVL, with the results of our methods, one can see that we are roughly in the same range precision-wise, but regarding outliers, we perform quite a bit better than the acoustic sensors. Here you can see some of the depth images obtained from the true depth network. First row is the input RGB image, second row is the output of the true depth network, the third row is a retrained version of the true depth, and the fourth row is the DVL measurement in color. One can see here that the true depth does recognize the shape of the net, but it doesn't recognize any fish in front of the net. And this is due to the fact that the FFT method only detects the net and nothing else. As mentioned, by combining the FFT points together with additional sensor data, aka velocity estimates of the DVL, we were able to obtain global pose estimations and thus able to recreate the three-dimensional trajectory of the vehicle. Combining the obtained depth images with the global pose estimates, we were able to utilize the WaveMap method to obtain three-dimensional volumetric maps, and we were also able to project the RGB images onto the cylinder wall to obtain a visual representation of the net pen. As a conclusion, our results show the possibilities of integrating FFT, true depth, and WaveMap method for underwater and fish farming applications. But we also showed the potential of future development of the combination of those three methods.
Thank you. Next presenter is Latif Hassan. Are you there? Yes. And welcome back. You will present for us autonomous underwater robotic system for aquaculture application.
Hello everyone. So based upon our previous source, so we have used vision-based model for aquarium inspections. And from our results, we found that the vision model performance mainly depends on the ROV positions. So if the ROV is relatively very far from the net, and the vision model perform very poor for the detection task. So similarly, if the ROV is very close to the net, so the vision model doesn't recognize the proper net abnormalities. So to avoid these problems, we need to make sure that the ROV is relatively in a very desired position or in a very optimal position so that it can capture the net clearly and so that the vision model can perform the detection and inspection task. So in this regard, we present the coupling of ROV with vision models, both for the keeping the relative distance with respect to the net and performing the detection task. So the basic framework or architecture of our work is this. So we have basically two modules. One is the ROV side and the other is the top side server or personal computer. So the ROV has different sensors like camera, DVL, and thrusters. The topside server computers is connected with the ROV through the Wi-Fi network. The ROV sends the real-time imaging, and on the computer sides, there are two modules. One performs the vision activities, and the others perform the detection task. So from the basic traditional computer vision activities, we are estimating the current distance of the ROV with respect to the net, and based on the desired distance and the current distance, we are sending the ROV moving command backward forward, and the other module perform the detection task for the net inspection. So this is the overall structure of the framework. So here are some results. So the left side graph shows the distance estimation of the ROV with respect to the net during the experiments, and the right side shows the detections of the net inspection, like net hole detection, vegetation. So these are the primarily results of the framework. And based on these works, we have different sort of general publications. And that's time. Thank you.
Thank you very much. Okay, one speaker more from this group.
Yeah.
Now we're going. We're almost out of electricity. Of the acoustic semantic slam with unknown object in underwater environment. Karan Singh, are you here?
You're the alert.
We are overdue. I hope to be able to welcome you. Please try to make a presentation. I hope we have sufficiently electricity power. Karan, the mic is yours.
Yeah. I'm not sure if this one worked.
Yeah.
Okay,
Okay, I'll just
arrows.
Okay. Hi, everyone. I'm Jung Seok Hong. I'll be presenting our work of the acoustic semantic slam with unknown object in underwater environments by Karan Singh, myself, Whitney Kima, and John Leonard. So as some of you know, underwater semantic slam is crucial to enable more autonomous behavior in underwater for underwater vehicles. However, the accuracy of underwater semantic slam is way behind those of aerial or terrestrial semantic slams because of the following reasons. First, we don't have large data set that has wide range of semantics. Additionally, we have additional sensors on top of like other like usual noise, such as optical caustics that you can see on the left side, and then also reflections. And then even in the sonar sensors, there are acoustic artifacts and multipath effects. So to accommodate these shortcomings, we proposed this pipeline where we utilize optical and sonar information together to estimate 3D position of the object for unknown object. So to accomplish this, we first perform unsupervised segmentation from RGB images. Then we combine with the range information from the sonar sensor to estimate 3D position. And then also we use vision foundation model to extract feature embeddings from the RGB image of the object. Then we combine this information for data association. And then we apply proposed data association with ICM2 pipeline. And then that's how we estimate our final map. And then this is our qualitative result. As you can see, these objects are all unknown prior to the deployment, but you can see that our approach was able to map those objects relatively accurately. And then I want to share this example, if I can play this video. Yeah, so this is a very short video how our approach can fix the automatic drift using the object-based feature. Yeah, probably just embedded as a photo. Yeah, I don't think we can show this video, but we have a presentation tomorrow, and then we also have poster today and tomorrow. So please come to the poster, or you can just talk to me. Thank you.
Thank you very much, Karan. So the next one is online. It is Kashyap Joshi presenting 3D water quality mapping using invariant extended Kalman filtering for underwater robot localization. And after that, we have one presenter that has been very patient, waiting to be the last one for today. And after that, we go to award. While Sven is struggling, I want to thank the sound man or man for today, and the video man and you have been doing good, Sven.
Thank you. I don't get in contact with this this thing here. It's not showing up. This one. I not know why.
The
but
internet is ready for
give me the
yeah, but I have the other one on this one. But for some reason, it's not detecting that. So
Should we try the?
let's swap the presentation.
yeah. So now we go for presentation. The last one.
The last presentation will be the second last, or perhaps the last, if we. At least I want to welcome Ayelari, Emily Lode,
Yogang Singh.
Yogan Singh. Yogan Singh, thank you for coming. You are going to present towards design and development of a low-cost USB for aquaculture water quality monitoring in shallow water environments. Thank you.
Welcome, everybody. Thank you for being patient for the last presentation. My presentation is going to be short and concise. We talked about platforms, we talked about vision algorithms, we talked about a lot of things. I'm going to talk about how we can vehicle design things at a low cost for those places where the money is a constraint. And that's what we are going to focus in this presentation about. The challenge in most of the aquaculture industry is that aquaculture industry grew in the last 5 years at 189 million metric tons. Out of that, 89 million metric tons come from the developing nations. And that is because of the requirement of the local industry. Now, the local industry in these developing regions basically have two major issues. One is the labor shortage, and another one is the cost of their operations. So therefore, shallow water environments become a very major issue when we are operating in these developing regions. Therefore, the need comes up for developing a cost-effective, easy-to-deploy agile robotic solutions. Mobility in these constrained environments is another challenge. So therefore, we need to develop low-cost USV which can be effective for water quality monitoring in shallow water environment, because water quality is a very major aspect in aquaculture industry because of the impact it has on the health of the environment and the species which are operating there. So our design is very simpler, very basic robotics we come up with, 3D print all our parts in the lab itself. Bring down those parts together by making use of the epoxy resins and PLFA filaments, along with making use of carbon fiber rods to basically connect and create a hull model. We basically designed two platforms as a part of it, but our presentation is only presenting one, where one of them is like a hovercraft style and the one is an underwater style. Overall, the platform is 5 kgs in weight, smaller in size, easy to deploy, basically very small in our velocity side, so smaller in speed. 5 meter maximum speed goes up to 5 meters per second. Hardware design, high-level control. We are basically making use of IROS Ubuntu systems, and basically at the low-level control, very traditional Arduino's platforms. Our ROS architecture basically comprises of ROS files, launch files, along with the connections and their subsequent interactions, which we are making use of Wi-Fi and 4G technologies. Overall, the final design comes up there in form of a prototype, a working prototype, basically for testing the maneuvering capabilities in shallow waters. The major requirement is that car be compliant to the International Maritime Organization requirements. IMO has set up the evaluation criteria for maneuvering for most of the vessels, and this comes up from my knowledge from the marine engineering, being a marine engineer and being an architect. Basically, that you need to calculate the advanced and tactical diameters, and for a proper turning within the constant environment where humans cannot reach, and basically for those shallow water applications where we need the species to be understood, we need to make sure that the turning circle along with the advanced and the tactical diameter should be within those ranges shown there. What we tried to do is that we did the test on the port side and the starboard side for these maneuvering tests and try to calculate the basic parameters for advanced transfer tactical loss of speed turn, time of change of heading on 90 degrees and 180 degrees. And for these three tests, we basically have the measured as well as the actual criteria present to us. We realize that most of our robotic applications do not have the maneuvering capabilities which they require in shallow water applications, and therefore we need to develop better vessels, and we are working in that direction. This is just a preliminary work. In November, we are presenting another work related to our vessel maneuvering, again, an international ship conference, and where we are going to present some iterative work on these ones. So that basically sums up our result. This is our USV, which is in motion. And basically what we are trying to do here is trying to show up one of the test results which are there for these maneuvering simulations. Very easy to deploy, remotely controlled, and we are doing it in one of the reservoirs in Sheffield in the United Kingdom. Thank you so much for listening to us.
Thank you so much. Are we trying?
Trying one more time. The different
One more time. We're trying. And after that, it's Helene show.
Hey everyone, so we are from the University of Maryland, and today we will be presenting our work on 3D water quality mapping using invariant extended Kalman filter for underwater robot localization. So diving right into it, you can see that there are some challenges with traditional water quality mapping methods. The first one being a boat where you don't have a lot of depth variability since you can't lower the sensor beyond a certain depth. And the second one being human divers, which are slow and you have limited time on it depending on your scuba tanks. But our method tries to counter these points by doing water quality mapping using a robot. So the only challenge here is underwater 3D localization, as you can see on the right. Since we operate in aquaculture environments, the turbidity is very high due to shallow water, and this leads to vision-based SLAM methods not being very robust for the same. So to counter this, we need a method to have a intermediate pose estimate between like two good vision-based SLAM readings, and that's why we take advantage of the invariant extended Kalman filter, which is a modified version of EKF, and it's robust to sensor noises, as well as it provides a very major contribution of being a model-free approach to handle our nonlinear dynamics. So we use the AMU readings as inputs here and the AHRS and DVL readings to correct the estimate. And our pose is initialized using a GPS reading. So to test this out, we have modified the Blue ROV platform by retrofitting it with GPS and DVL as well as a multiparameter XO2 sensor. So you can see on the right there is a flowchart on how this methodology works. And during the experiments, we frequently resurfaced it by leveraging different sensor readings in different. So we tested out this method in the Chesapeake Bay in Maryland. And we noticed that when we compare it against the GPS reading for ground reference after surface tracing, we had an error of 1.5 meter for like a 100-second run and around 3 meters for 300-second run. The variance was pretty low as well, which showed us that okay, like this is good for us in an intermediate scenario if we want to just look at it for like just even 10 or 20 seconds or even like a long-term vision occlusion. Hence, we could use this for a water quality analysis, which we compared against the EXO water quality sensor that we have, and we plotted the readings with depth variability for temperature, TDS, salinity, pH, chlorophyll, TSS, all of it. And we could notice like good results with it, which gave us like results for like a variable depth analysis of water quality. So for future work, we can have a more hybrid estimation approach with combining optimization as well as a filter to get an accurate but a fast method, and then combine this with vision with SLAM methods and see how well it works. Then we want to look into real-time integration with the sensor so that we can have like a autonomous navigation methodology to move towards more like specific parameter values in the way. So that's all from us, and if you have any questions, let us know. Thank you.
Okay, I think that the welcome party is starting very well, very soon. And it has been a long day, so we're gonna skip the panel discussion, but you can find us all within the conference to discuss any questions you have. But I would like to move and present the awards because in this workshop we have been really privileged to have two technical committees that are supporting two awards and also here in robotics and AI. Well, Trinom is putting up the presentation.
Did you send it to me on email?
Yes. I would like to thank everybody, especially the invited speakers and all the spotlight presentations. If you have energy, before going to welcome, join the poster sessions if you have any discussions for the presenters or find them on the welcome reception. And now Simon will put the award. Yes. So we have three awards. One from just go for it. So in this workshop, the first award goes to yes, Dr. Guillemot on the work Best Vision methods dedicated to aquaculture, and it's supported from the technical committee on computer and robot vision. And I can say that independent committee has been assigned to decide this, so it was not the organizers taking this decision. So this is the first award. The second award that is goes to Dr. Yossi. They were not able to join, but we will send them email and inform that they have the best paper award framework for autonomous navigation and control from the Technical Committee on Algorithms for Planning and Control of Robot Motion. And the last one, which is the best conference paper award, will go to the paper that is presented from Dr. Hong and his team from MIT, Kuran Singh. So, and they will be getting award from the Frontier in order to submit the next journal if they want on the special issue or any other issue. I would really like the two of the people that are here that took the awards just to take some picture together here, if you would like to. While you're coming to take the picture, I want just if you can switch to the previous presentation of the workshop. It's really important to acknowledge the people. So I want to show two things here.
Acknowledgements?
Yes. So this is the technical committee on computer and robot vision. So follow them. They have, and all the committees, they have all their things. And I would like to tell that there is this special issue. So submit your work if you are working in marine or underwater domain with deadline in March, and talk to us, to organize this for more details. The last is finishing this workshop and saying that we need robotic solutions for aquaculture. So let's work together and realize what we said, biology and technology. Thank you for staying. It was such a great workshop. And let's take the picture with the award winners together. Thank you, everybody, for staying.